You all. I am immensely delighted to have among us today in the inaugural program of the 5 days course on advanced and futuristic manufacturing process. The chief guest, Professor Anil D. Sahasrabuddhe, Honorable Chairman of All India Council of Technical Education. As a guest of honor, we have Professor Amitabh Ghosh, Platinum Jubilee Senior Scientist of the National Academy of Science India and former Director of IIT Kharagpur. We have among us Sri Ajay Chaudhuri, although he is not present, but he has shared a video of his lecture. We have among us Dr. Onkar Rai, Director General, Software Technology Park of India, Sri Shyam H. Arjunavatkar, Honorable Chairman of BOG, National Institute of Foundry and Forge Technology. We have amongst us Honorable Vice Chancellor of Jharkhand University of Technology and Raj University and other universities of Jharkhand. We have respected directors, principal and representatives of the technical institutes in and around Jharkhand from different research organizations and representatives from industries. We have among us esteemed official of Jharkhand government and union ministries, the distinguished speakers in different sessions of the course, honorable member of BOG and Academic Council of NIFT, faculty members and alumni of NIFFT, and especially participants of the course, which is 745 in number. It is my great honor and privilege to extend my heartiest welcome to you in the inaugural ceremony of the 5 days course on advanced and futuristic manufacturing process. I would also like to express our sincere gratitude to all of you for your gracious presence amidst us today, which is indeed a tremendous encouragement for the NIFT fraternity. Now, I would like to request Sri Shyam Arjunavatkar, our Honorable Chairman of BOG, to preside over the session and to permit Dr. Himanshu Khandelwal, host of the online platform today, to coordinate the session. Thank you very much.
Oh, well. Thank you, Professor Partha Jadavadhe. It's certainly my pleasure to request Mr. Himanshu Khandelwal to please proceed with today's proceedings. Please go ahead. Thank you.
Good afternoon, all. So I'll request now Professor Amitabh Ghosh to please address all the audience. Professor Amitabh Ghosh, you can maybe project yourself and share your screen. Just give us a second. I believe Professor Amitabh Ghosh, I think, has just got disconnected.
He has still not been seen joined, actually.
Yeah. Actually, he has joined. I don't know. Somehow now he is disconnected. We are just connecting with him. So in the meantime, will Shri Ajay Chaudhary sir, due to some event, actually he could not attend this session. So he has shared his video clip with us. So I'll just share that.
That's fine. That's fine. Please go ahead.
Yeah.
ठीक है हे का रिसीव है याचा संबंध आहे मी बोललेलं त्यांना ऐकू येत नाही याचं काहीच ऐकू येत नाही.
Sir, not audible. I think your microphone is muted. Unmute yourself, sir.
Yeah, just give us a minute. No, it's unmute only. It is working, no? Is it audible, sir?
Yeah, now I can listen, but the presentation is not. We were not able to listen to the presentation. Your voice is. We can listen to your voice, but not the presentation.
Okay, just give us a minute.
ह्याचा प्रेझेंटेशनचा आवाज कोणालाच येत नाहीये तो प्रॉब्लेम नाहीये पण इथं हे काय
It's not audible.
नाही मला आवाज ऐकू येतो पण हे हा प्रेझेंटेशनचा आवाज ऐकू येत नाही त्यांचाच प्रॉब्लेम आहे कुणालाच ऐकू येत नाहीये बहुतेक जातोय कारण मी बोललेलं मगाशी ऐकू आलं त्यांना पण फक्त असं हे दिसते म्हणल्यानंतर मी जरा थोडं कॉशियस झालं.
Yeah, so just apology for this. I don't know, some issue, technical issue there. I'll just resolve that. So meanwhile, I'll request Professor Amitava Ghosh to please address us.
Thank you. Am I audible to the all?
Yes,
Can
sir.
you hear me?
Yeah.
Yes, sir.
Okay.
Yes, sir.
Thank
Yes, sir.
you.
Yes, sir.
I think it is very nice to see old familiar friends, Professor Shastri. We are seeing you after a long time.
Namaskar.
I hope you are all fine.
All fine. Namaskar.
So, to begin with, I will also welcome the distinguished members and the esteemed colleagues of NIFT and the participants. And I must thank NIFT Ranchi and the director of the institute and the members of the organizing team for arranging this timely event and inviting me to participate. Now, you all know that it is a recognized point that a country like India must excel in manufacturing, as this activity plays the driving role for the progress of economy. The attention to this has already been drawn by our Prime Minister in his Make in India slogan. The danger of making our economy primarily dependent on the IT sector is already understood by you. Now, furthermore, emphasizing management over real manufacturing has also been found to be detrimental to the progress, as it has been painfully realized by a country like USA. Now, being the only national level institute dedicated to manufacturing, I think NIFT has a very special role to play. And under the able leadership of the present director and the board of governors of NIFT, it has started many programs and organized this event, which I consider to be extremely important and timely. It is heartening to note that NIFT has been able to involve a large number of national level leaders in the field from all over the country. This short course is well planned and it contains about 12 lectures, each one being 1.5 hour duration. So advanced and futuristic issues of manufacturing being the main point, I think it has to be kept in mind that discussing the future scenario is very important, as that can help us in planning and charting the course of action, both in academia and also in the industry. Now, briefly, I'll mention the program. First, I think it is in the coming years, we all recognize that while developing advanced manufacturing processes, it may not be possible to conduct actual experiment to develop such processes. In all such situations, the primary role or primary aim is going to be extensive modeling and simulation. Only through that we can really make a particular advanced process complete. Now, I think we have amongst us Professor Uday Dixit, Professor of IIT Guwahati. He will introduce this subject, being an active researcher in the field. Another point which I think I'll mention in my second lecture or first lecture, that miniaturization is going to be a major objective in the coming days. Now, it is expected that this will be the primary route through which we will enter the impending third industrial revolution, according to many experts. Now, Professor Subhas Joshi, Professor of Mechanical Engineering, IIT Bombay, will present the various issues related to micromanufacturing. Along with the progress in science, many new fabrication processes are being continuously developed. These newly developed processes are generally called, or rather they form a class of manufacturing techniques, usually given the title non-traditional processes, although many of those have become a part of the regular fabrication processes in the industry. But the general trend, how a fabrication process can be developed by using basic scientific principles, will be discussed by Professor Prashant Kumar Mishra, who was a former professor of mechanical engineering IIT Kharagpur. Now he teaches at College of Engineering Pune as an emeritus professor. In many manufacturing processes, perhaps the most, thermal issues play extremely important roles. And without a proper understanding of these issues, the desired results are not generally achieved. And so it is essential for those who are researchers in the field of manufacturing, such issues must be understood clearly. Professor Pradeep Datta, Professor of Mechanical Engineering of IISc Bangalore, a national level leader in this field, will apprise the participants on this subject. Dr. Debashish Bhattacharya of Tata Steel is not only an expert on advanced materials, but as I have experienced once, he is an outstanding speaker. He will discuss the challenges of the new generation materials posed to the manufacturing processes in the coming decades. IIoT is considered as the enabler for advanced manufacturing, and this new and exciting topic will be presented by Mr. Rahul Segal of Design Tech Systems Private Limited, Bangalore. One of the major components of the primary processes for manufacturing is metal forming. Now, many new developments in this area has made it possible to customize the product in a very cost-effective manner. This mass customization of the products of metal forming will be taken up by Professor N. Venkata Reddy, Professor of Mechanical Engineering, IIT Hyderabad. Now, one of the major tools for advanced manufacturing is the powerful laser beam, we all know. Now, initially, it started with simple cutting and welding jobs, but now it is becoming an increasingly major issue in the field of advanced manufacturing, starting from normal manufacturing to even additive manufacturing. We have amongst us a world leader in the subject, Professor Indranil Manna, Professor of Materials Engineering, IIT Kharagpur, and the former director of IIT Kanpur, to present the various facets of lasers in advancement. Foundry processes form a major component of the primary manufacturing family, and the participants will be exposed to the various advancements in the field of foundry technology by Dr. Naga Hanumaya, who is the current director of CMTI, also a senior scientist from Central Mechanical Engineering Research Institute, Durgapur. Many new areas are coming in the field of forge technology, like semi-solid processing, massive forming, etc., are some of the examples. And the emerging trend in forge technology will be taken up for discussion by Dr. Vasan Tische of SAMI Consultancy, Maharashtra. Now, to begin with, the course will start with an introductory lecture by me. It will be an overall view of advanced manufacturing and the trend of the current progress. This will be again followed by another lecture today itself, which will be devoted to a specialized topic, the scaling laws, the science of miniaturization. Both these introductory lectures will be delivered immediately after the inaugural session as per the program. It is expected that the participants of this 5-day short course will benefit immensely and can use the gained knowledge in their respective fields of activity, be in academia or industry. I again thank NIFT and the organizers of this timely event for organizing such a major program. We all understand that with this new situation, many things we are learning, because at the age of almost 80, I have to learn now how to deliver a lecture through online, etc. There are certain advantages also I find, that now you don't have to travel. The organizers don't have to arrange for local hospitality, local transport, and the speakers will be needed only to have the shirt, not the pant in such cases. So I wish all of you a wonderful and useful time during this short course, and thank you very much. Jai Hind.
Thank you.
Yeah. So yeah, we will once again try to listen Shri Ajay Chaudhary, SCL founder. Just give me a minute. I'll just share this.
Himanshu, is it a recorded lecture or is it
Yes,
live?
sir. It's a recorded lecture.
Something still we are not able to listen properly.
Yeah. Somehow actually I'm sharing his. इससे नहीं जा रहा. Yeah. So I'll request Dr. Anup Sood to please try to present from his system.
Okay.
Just to give us. सर एक बार आप देखिए तो नहीं तो आप. So yeah, sorry, apology for that. We are not trying to, get Shri Ajay Chaudhary's voice on to all of you. So I'll request till that time Dr. Omkar Rai sir, Director General STPI, to please address us.
Thank you very much. The dignitaries on the dais, Professor Anil D. Sahasrabudhe ji, Shri Sam H. Arjun Wadkar ji, Professor Amitabh Ghosh, IIEST Shivpur, Director NIFT Ranchi, Professor Parth Pratim Chattopadhyay, Professor P.K. Mishra, Professor A.K. Sood, other participants, respected Vice Chancellor who are said to have joined this platform. I'm very glad to be here, and I'm very excited and encouraged with the kind of initiative that NIFFT has taken, particularly to have a workshop on advanced and futuristic manufacturing processes. I think at a time when India is trying hard to reestablish, reimagine its manufacturing success story, and when India has aspired and resolved to become Atmanirbhar in all aspects, this kind of workshop with the focus on manufacturing automation is very important. For long, the collaboration between academia and industry and a kind of knowledge sharing, sensitizing the factories, the owner, the engineers about the importance of adopting the modern skills, adopting emerging technology in terms of making manufacturing more efficient, more productive, has got a lot of importance during last few years for this country. I would say that India has been home to a lot of growth in terms of IT services industry, and these are the services industry, particularly the IT services, actually has been delivering these kind of services to their customers, and the entire transformation that has happened all across the country in terms of Industry 3.0 has been actually powered by the IT industry of India. Even in terms of the transformation, the growth that we are witnessing in terms of Industry 4.0 actually is being powered by Indian IT industry, Indian intellect, Indian knowledge systems. And that is being, leveraged and capitalized by the advanced nation in terms of manufacturing. We are a very large country with a lot of young boys and girls coming out of our institutions, educational institutions, engineering colleges. And therefore, there has been a need for a long time to make sure that we equally do good in terms of manufacturing technologies. Apart from making present manufacturing bases more efficient, more productive, we have to prepare a great manpower, great skilled people who can take care of the entire upcoming manufacturing need of this nation. And we could supply them skilled people, well versed with well versed with the activities and process it at all level. And therefore, this is very important that the academia takes a lead, and it works very closely with the industry in terms of making things seamlessly interactive and collaborative. And if we look at this 5 days program, about which Professor Amitabh Ghosh has very beautifully introduced, I am very happy that this kind of collaboration has already started taking place. We know that all these technologies are going to make the Indian industry very efficient. And therefore, the benefit of this technology has to even reach to MSME sector, apart from the heavy manufacturing sector. And therefore, the democratization of these technologies becomes very important. And therefore, the kind of technology, we talk about Industry 4.0 technology, apart from teaching students about that, apart from skilling people from industry and outside, we have to create a huge content using AR and VR technology, emerging technologies, so that that content, as Professor Amitabh Ghosh has just referred about one topic that is being discussed, that simulation and modeling. I would say that people need more collaborative and simulated environment, a kind of interactive and immersive experience in terms of understanding the factory floor, the processes, and without even visiting the factory floor, they could understand what is this, automation is all about, what it looks like, and what goes into it in making things Industry 4.0 ready. And therefore, one more thing that is becomes very important is that not only we have to, improve the things we have, not only we have to, train students that are joining our engineering colleges. We have to create a kind of skill platform where large number of people, right from ITIs, polytechnic, engineering colleges, and all those people who are actually unskilled labor who are employed in factories, can be afforded with that kind of immersive experience of feeling the factory floor and feeling the requirement. And that is how this kind of skill set is also required to be imparted by automated means through a platform. Apart from these things, I would also say that one very important aspect has to be taken care of by the industry and academia and the leaders in these sectors, that they must come out and join hand with the startups and pass on their knowledge and expertise to them, mentor them, so that they could solve the problem that we face today. It's a matter of utmost importance that the factories, the enterprises come out with the list of problem statements, the problems that are to be solved, and share the same thing with the young boys and girls of this nation. Whereas the professors, learned professors, who are so well versed, on par with the rest of the world, in defining the new technology, teaching these new technologies, and understanding, realizing the potential, they should actually come out and join hand with the industry and work with the young boys and girls so that they could solve the problem, ideate, and bring new technologies, platforms, products for actually revolutionizing the entire manufacturing landscape in India. With these few words, I must thank IIFT for inviting me and affording a great opportunity to listen to the eminent and experts in this very field, and for organizing this very important 5 days workshop, which I am sure that it is a kind of leading workshop or kind of pioneering workshop with these kind of content in place. I'm very sure that other institutions would also collaborate and follow the suit. And India would be actually a place where we'll be able to impart and bring almost all the people, relevant people on the platform for sharing of knowledge, learning, and moving ahead with the kind of force that we have. Thank you very much.
Thank you.
Thank you, sir, for your address.
I'm very happy to be part of this function to launch the course on advanced and futuristic manufacturing process at NIFT. I had the pleasure to be part of the NIFT family for a very short spell of time when MHRD had asked me to step into chair and NIFT till a new chairman is appointed. During that period, we had a committee led by Professor Amitabh Ghosh that helped us create the plan for next 5 years for NIFT to take the institution towards Industry 4.0. Well, if we look at how manufacturing started, and Industry 1.0 was started with pretty much mechanization, steam and water power. The next one was Industry 2.0, and that adopted mass production and electricity. Industry 3.0 was due to electronics and IT systems, and of course, automation. And now Industry 4.0 has been created with cyber physical systems. Industry 4.0 is a blend of advanced and analytics, big data, robotics and automation, AI, and Internet of Things, and of course, process digitization across the whole business value chain. The benefits of Industry 4.0 are enhanced production capacity and quality. Here, data analytics will ensure prediction and prevention of defects. Shorter production cycles, reduced trying to market. Better experience for customers and employees. And tighter supply chain and reduced lead times. According to McKinsey, if Indian companies adopt Industry 4.0 across functions, they can increase operating profit by 40% at less than 10% of the planned capex. The demand for engineers equipped with knowledge of Industry 4.0 will increase as India becomes the next manufacturing hub. Due to COVID, a large number of companies want to move out of China and have another base. India has the opportunity to get that base. A lot is happening in electronics manufacturing due to very attractive government policies, and we will see similar policies to support an Atmanirbhar Bharat. This will benefit NIFT as the institute will now be moving towards Industry 4.0, teaching and practice. This is wishing the new course all success. Thank you.
Yeah. Apology for the inconsistency which we were having, the technical difficulties. I would like to thank Sri Ajay Chaudhary sir for sharing his video clip with us. Now, I would like to invite our Honorable Chairman Sri Shyam H. Wadkar sir to please address us. Sir, over to you.
Yeah, well, thank you, Himanshu. Well, it is my pleasure to be here among the galaxy of this panelist. Professor Amitabh Ghosh, Dr. Omkar Rai, Professor Abhay, then Chairman of AICTE, Professor Anil Sahasrabudhe, and people in the audience of the esteem of Vice Chancellor of Jharkhand University and all fellow panelists. It's really my pleasure to share my thoughts on this program of advanced and futuristic manufacturing process organized by NIFT. The NIFT BOG, inspired by my predecessor, Mr. Ajay Chaudhary, has determined to take up this subject, which is very close to that. And I can say Mr. Ajay ji is from the IT industries, you can say the dawn of IT industries, and the Midas touch of him has really made us to change our thinking pattern for the manufacturing industries. And now we are suddenly sure that as fast as possible, we'll take up the mission to change the curriculum of NIFT as needed for the industry advance of 4.0. The NIFT decided to embark for advanced and futuristic manufacturing program to make students competent and thus to prepare the requisite curriculum for my experts panel led by Professor Amitabh Ghosh. Just now you heard from him, and he also referred to the same experts panel. And he has got a team of learned faculties. He has a team of learned faculties who are with us for the program. They are experts in their respective subjects and also passionate for the same. I myself have experienced this passion during our meet at expert panel. I am happy to note their interest continues, and I am thankful to all of them that they're with us for this program. To my knowledge, I'm not from academia. Certainly, I'm a hardcore foundry person, rose from the shop floor. And then when we think of advanced manufacturing, what the first definition, what I feel is the production with the perfection. Then this may be of any commodity, forge or cast components. In today's era of advanced manufacturing, the machines speak to each other and make the production as desired. That is what we look forward for the advanced and futuristic manufacturing. The language the machine speaks is a digital language, and they don't dwell in the past and future, but speak in present. That is the real time. The alphabets they speak are various machine and process parameters. The dialogue of these parameters, you can say the interaction of these parameters is the ultimate result of the manufacturing process. This is the ultimate statement of machine language. And the beauty is that these hypotheses are stored in a memory of machines. This is knowledge. This is a knowledge repository, and machines making use of this knowledge repository leads to artificial intelligence. As I'm from the foundry background, I can say that there are several sub-processes involved in variable in the foundry cast making process as such, and there are several variable parameters, process parameters are there, and for each sub-processes. So that becomes a case of complex variables. And to get the right desired casting, we need to control all these variables on the real-time basis. And that is the only way to lead to the zero defect manufacturing. As on date, the foundry industry or for that matter, engineering industries they're tending towards the zero manufacturing. There are hardly any, there are very, very rarely some enterprises that attend to the zero defect manufacturing. But the phenomenon of advanced manufacturing is the only thing for the sustainable growth of the enterprises. And I'll just cite, the sustainable growth is one virtue of the advanced manufacturing, but that is not enough. Why it is needed? It is needed to care for the mankind also. I can cite one small example how it cares for the mankind. That is, if you consider a normal foundry casting production, the rejection percentage are from 3 to 10%. So on an average, the casting production in Indian foundries is around, so you can consider the rejection levels are around 5%. And we in India, we produce around 12 million tons of castings. And if you consider the 5% rejects, that goes to around 6 lakhs tons of castings. So just imagine the volume, what kind of volume it speaks about that. And for 1 kg of casting, if you produce 1 kg of a good casting, it emits the 1 ton of CO2, that is the greenhouse gas. So just imagine if you save, if you go towards the zero defect manufacturing, if you save this 5% of the rejection, and only the greenhouse gas effect or the carbon footprint, the kind of volume what you are going to save for that. So the advanced manufacturing is there for the sustainable growth is one part of it, profitability is other part of it, but it certainly serves the humankind or the mankind. As just now, Mr. Rai Saab has referred to the manufacturing requirements with the IT industry and all. In Eurovision 2020, they had given the emphasis to the manufacturing industries. Otherwise, you are aware that the European community was more interested in making the investment in other countries to get the returns of their investments. But in turn, they found out to generate the wealth and to care for the employment, they need to have the manufacturing setup in their own countries and to enhance the manufacturing activities in their own countries. And for that purpose, to make the comfort level, they take full advantage of IT. What the terms refer to us as a Internet of Everything, or data analytics, big data analytics, that leads to Internet of Everything, and then that gives, ultimately that gives the real-time information and the total digital control of the manufacturing process, gives the enhanced comforts to the operating people, and that is what the European people, they have understood, and they have gone to that, and they have already progressed in that direction. Rather, they have already attained a substantial success in that direction. We in India, we are making that we are always under impression that our manpower is cheap and labor is cheap and costs are so less and all. But over the time, that's not a debatable at all. We know what the real facts are. So let us not get into that, but to think of these advanced manufacturing processes and the futuristic planning, it doesn't confine to only 3D or IoT. Ultimately, we have to take care of entire gamut of the manufacturing processes, and that could include the handling of raw materials, logistics, and reduction in the WIPs to the reduction of WIPs. So the industry is fully aware of it. If you ask to any average industrial forum or anywhere, if you get in touch with the industrial forum, they will speak that they want to attain all these things. And but as a whole, they're not very clear about the roadmap. They're worried that whether they're going to get the competent people to manage this or not. They're really worried to what extent they can succeed and how much time it will take. And they're precisely, as I said earlier, Mr. Ajay Chaudhary, he has given a Midas touch to NIFT thinking, and then we have started thinking on those lines of making the curriculum which will make our students competent engineers to become to satisfy the need of the engineering industries or the manufacturing industries. I'm sure Dr. Sahasrabuddhe and AICT, they will also appreciate these efforts of going to that direction. And though we are planning for the 5 years, but we will make every effort to see that how we reduce this time frame, and how we make and how we produce the students. Produce is not, I'm from the manufacturing, so the word produce came to my mind, but we'll prepare our students to of that caliber that they will be advantaged to march towards this industry 4.0, and which will be beneficial to our engineering industry's growth. The advantages of this are already discussed. They are very well elaborated by Mr. Roy, Mr. Ajayji, and Professor Ghosh. And I'm sure the guidance from Professor Ghosh will continue in this respect, in this direction. And we look forward to all this team of experts to be with us till we attain the benchmark in this direction. Well, with these words, I wish this program a very good success. And I once again extend my thanks to Professor Ghosh and his team of learned professors. Thank you very much.
Thank you, Chairman, sir, for your kind words. Now I would like to request Honorable Chairman AICT, Professor Anil B. Shahbudhe, sir, please address us. Over to you, sir.
Yeah. Good afternoon, everyone. Most respected Professor Amitabh Ghosh, eminent academician, former director of IIT Kharagpur, professor at IIT Kanpur, and now Professor Emeritus at IIEST. Sri Shyam Arjunwadkar, Chairman of Board of Governors of NIFT Ranchi, Professor Partha Chattopadhyay, Director of NIFT Ranchi, Sri Ajay Chaudhary, Founder HCL, who gave eloquent remarks about the Industry 4.0, Dr. Onkar Rai, Director General STPI, my good friends who are there either on the panel here or subsequently who will be speaking, Professor P.K. Mishra, with whom I was associated when I was in College of Engineering, Pune as director. He still continues there at this age teaching, and his practical abilities are phenomenal. Then my colleague in NERIST, Dr. M.K. Tiwari, then in IIT Kharagpur and now director of NITI, Dr. Uday Dikshit, my again colleague from IIT Guwahati, Dr. Manna, Suhas Joshi, Venkat Reddy, All of these are good friends of ours, and it's very good to meet, if not physically, at least in the cyberspace. Professor Amitabh Ghosh rightly pointed out, in this, you only have to wear in the good shirt or a suit, and what is there we do not know. I think that is a joke which he made, but certainly the advantage is that we have not met for years, but we are in a position to meet on this occasion. A very important occasion. NIFT has taken a lead in organizing a short-term course on advanced and futuristic manufacturing processes at a very appropriate time, from two counts. Number one, the Honorable Prime Minister started speaking about Skill India, Digital India, Make in India, Startup India. But this year, quite often, because of COVID times and the economy being down, to lift it up, we are talking about Atmanirbhar Bharat from two perspectives. One is we are heavily dependent on many articles from China, including ordinary things like toys, Diwali gifts. They all come from China, and therefore we need to be self-sufficient in terms of manufacturing all such low-end articles. At the same time, on a higher end, very sophisticated, whether products and processes, machines also have to be developed within the country, and we should become Atmanirbhar. So this is a very important occasion for that. Secondly, interestingly, the new national education policy was rolled out on July 29th, and Dr. Kasturi Rangan has elaborately given a roadmap for what is to be done for the 21st century Bharat. I think very, very significant changes, almost transformative, game-changing, things are being talked about in that policy. I will touch upon some of those issues also a little later. But importantly, as rightly pointed out by Sri Ajay Chaudhary, we started off with Industry 1.0 revolution in the West, actually, mostly in the Europe. And from then, Industry 2.0 also took shape there itself. But during Industry 3.0, already America and Japan had taken the lead. But now in Industry 4.0, back to Germany, we have huge inputs which are coming in. Manufacturing based on Internet of Things, cyber physical spaces, data analytics, and different types of new ways of looking at production systems are being considered. But if you look back during our engineering days, we all started with conventional machining, and therefore some of the things which were not conventionally used, we were calling them as non-conventional. But as rightly pointed out by Professor Ghosh in the beginning, they are absolutely conventional today. But still sometimes in the books, we still call them as non-conventional. I think we need to change our books and properly, and then refer to them as absolutely conventional type of manufacturing processes. Then we moved on to numerically controlled machines, CNC machines, then also flexible manufacturing systems, use of automation, robots, both in the institutions as well as in the industry. And now we are talking about internet-based remote manufacturing capabilities possible. In the terms of different machining processes, we had electrochemical, electro-discharge machining, variants of that, foundry and forging, very important. NIFT itself is a specialized institute, only one of its kind in the country for forging foundry. And as rightly pointed out by Arjun Warkar ji, that a lot of mathematical modeling and how we can really develop processes which are zero defect free, and thereby the efficiency of the system will increase. We will also contribute to environment, we will contribute to sustainable development goals, we will reduce the losses, profitability increases, productivity increases. I think these are all possibilities which the futuristic manufacturing areas, processes will have to address. And in terms of also in welding, we started with gas welding, arc welding, TIG, MIG, then also acoustic based, vibration based, laser based, all of these welding phenomena. I think phenomenal changes have happened, and quality of products and processes have continuously been improving. And now we talk about micro machining and nano machining, all the more important in the world of IT, where chips are to be designed and manufactured. I think nano manufacturing has become order of the day. Use of high technology in terms of manufacturing chips is going to be the order of the day. While looking at all of this, sometimes we are saddened that in terms of IT, we are called IT superpower. In the late 80s and 90s, a lot of IT companies came up and we showed the world that there is a lot of talent in this country. But when it comes to manufacturing, somehow we had missed the bus. But it is the time to catch up. With the Atmanirbhar Bharat, with the new national education policy, it is the most appropriate time that we catch up in even manufacturing all variety of activities which are required. But if you little bit go back in history, in fact, I am very amazed that Professor Amitabh Ghosh, being a professor of mechanical engineering, after close to retirement, he started working on Saraswati civilization. I'm aware of some of his talks, very illustrative talks that he gives on Saraswati civilization, whether it is use of iron, steel, zinc, all of this was well known to our country, in our nation, several thousand years ago. And also we go back to Kerala, and I was gifted a mirror, which is called Aran Mulla mirror, I think Kannadi, they call Kannadi in the Malayalam language. It is a metal polished mirror actually. In a metal, you can see your face, and all done by hand. There's no machining process. So I think the kind of advancement that they had achieved in different domains is also worth taking into existence in our present day. But we should not be only happy with that, but how do we learn from that and take it forward in terms of doing research is what is very significant and important for all of us. So national education policy talks about the multidisciplinary universities. Many of our institutions started being very focused, engineering institutions, law universities, medical universities, and so on. And now the new policy talks about multidisciplinary. So that means along with the depth, we require a lot of width, and that is what is often required. And right from beginning, in fact, in IITs, there was emphasis on humanities and social sciences, physical sciences, whether physics, chemistry, math, always there. And some institutes like IIT Kharagpur have also changed, started from management to even law school, medical school, and so on. So I think in a way, some of the institutions have already started becoming multidisciplinary. It's very important, because none of the products which we see in today's world are from one particular discipline. You require the combination, collaboration of different disciplines. And that's why this particular aspect is very important. The policy also talks about a lot of flexibility in terms of multiple entry and exit. That means a student, when he joins a particular institution with a particular thing in mind, and after going there, he is finding himself not fit into that domain, there must be a possibility to change over or quit with certain certificate, with certain number of credits and so on. And also academic bank of credits, thereby a student can migrate from one institute to the other, capture those credits, keep them in his stock and make use of them as and when required. It's like bank balance. I think that is also being talked about in this policy. I think with this idea, one very significant change which has happened is in terms of two factors in higher education sector. That is about regulations and secondly about research. In terms of research, it talks about National Research Foundation, apex body which will fund large-scale projects for multiple institutions when they come together as a collaborative project. The amount may not be a restriction. Today, in the last 70 years, we have observed that many institutions, when they apply for projects, most of the agencies, whether it is then MHRD, now of course Ministry of Education, or DST, DBT, Atomic Energy Commission, that is BRNS, all of them have some limitations on funding. So for this kind of project, your limit is some 50 lakh or 40 lakh. And if you require more than that amount, so either you will not be able to do it, or you do haphazardly halfway through. And your basic objective of achieving certain outcomes are not going to be possible. Or you apply to multiple agencies, and if you are lucky, you will get funding from 2 or 3 agencies and you can satisfy the requirements. And then finally, you submit the same report all the places. And unfortunately, sometimes these agencies see with a suspicion that he has submitted the same report, but they don't realize that you required the total sum which was required, which was given by 3 different agencies. I think these challenges are likely to be addressed through a very large scale and directly Prime Minister's advisor, scientific advisor is going to chair this. So former secretary of Department of Biotechnology. So I think for funding, there must be no problem, whether it is in science, technology, or even in humanities and social sciences. So we will have a way forward in terms of research funding and leading to a lot of innovation in terms of our activities. Secondly, as I said, single regulatory body is also very important. Maybe NIFT may be facing sometimes some issues from AICT. I'm aware of that. And therefore, I would like to reflect this. In terms of regulatory bodies, we have had nearly 37 odd bodies. AICT regulates certain technical domain, but in that technical domain, along with engineering technology, we have management, we have architecture, we have pharmacy, we have applied art, craft and design, and hotel management. And now I don't know how technical education should have hotel management also one of them, or why pharmacy should be there. I don't know, but it has been part of the Act from 1987 onwards. While there was the existence of an Act of Pharmacy called as Pharmacy Act, and Pharmacy Council of India exists, there is a Act for Architecture and Council of Architecture exists. So if an institution wants to start a program in architecture or pharmacy, they have to come to both AICT and that institution. Fortunately, recently, Supreme Court has diverted this to only one of those agencies. That's a different matter. But I think this way, we had multiple agencies who were all going and troubling the institution. So the new policy looks at it in a holistic manner, having an apex body called what is known as HECI, Higher Education Commission of India, with 4 verticals. One vertical will take care of all regulatory function. Second vertical takes care of all funding function. The third vertical will take care of accreditation. Today we have 2 accrediting bodies, NAC and NBA. So there will be one single apex accreditation body. And fourth one is standard setting body, which will inform to the both accreditation body as well as the regulatory body that to start the college or to maintain good college and good quality, what are all things that are required? What are the outcomes desired? What kind of infrastructure required? What should be the faculties to enter? All of this will come from the standard setting agency. I think these are very clearly defined 4 different verticals under this one apex body. I think a lot of things will get smoothened out and many problems which we see today will get over. The last part is a lot of emphasis on skills and how do we relate skills, which is a vocational education, with the technical education or professional education on one side, and also imbibe teacher education. Because we have seen in the higher education sector, anyone who does masters and PhD comes into teaching profession in universities and colleges, and then some of them struggle for a couple of years, 3-4 years. Some senior faculty sometimes guides, sometimes does not, and they manage to become a reasonably good teacher. And some of them do not become good teacher for even lifelong till their retirement. I think therefore a lot of emphasis on teacher education has been done. And I'm very happy that under Professor Kincha, we had a committee and which gave us guidelines about what should be done for teachers when they come into the system and throughout their life cycle as a teacher, right from becoming a lecturer or assistant professor to professor and senior professor. What are their possible duties and functions that they have to do? How do they interact with students? How do they use ICT? How examination pattern needs to be changed from rote learning to what is known as Bloom's taxonomy based question paper setting. All of these are embedded in 8 modules, and unless one goes through that, the faculty is not going to be regularized in AICT approved institutions. And this is a big ticket change that we have already made before even the policy had come into existence. And there are many other things like training of faculty regularly in AI, IoT, machine learning, 3D printing, robotics. All of this is very important, significant for Industry 4.0. And therefore, in terms of this particular conference, I'm very happy that all these topical topics which are related with manufacturing, which will catapult India into a league of nations about in manufacturing as well, not in just IT and ICT. And that is what is going to be laying this emphasis. So thank you, all of you, for being with us and taking this particular conference forward. Training which you are giving to our faculty members. They will all engage with their respective students, and this particular workshop will be very, very useful for all of us. Thank you. Namaskar.
Thank you, sir, for your presence among us and these enlightening words. Now I would like to request Professor Anup Kumar Sood to please present the vote of thanks.
Thank you, Himanshu. First of all, I like to apologize regarding some glitches in audio video presentation. And it was actually a learning experience for us and we are enjoying it. We are learning daily new things. And I especially like to thank some participants who actually suggested us what to do, how to solve this problem. So I have been given an opportunity to give a vote of thanks. So it is my proud privilege to propose a vote of thanks in the inaugural ceremony of this short-term course on advanced and futuristic manufacturing process, which will held from 25th to 29th September 2020. The NIF fraternity is immensely grateful to Professor Anil D. Sahasrabuddhe sir, Honorable Chairman AICT, for making it possible to be among us today in spite of his extremely busy schedule. Sir, I take this opportunity to acknowledge your inspiration that has provided right guidance to us always when it was required at different occasions in our journey. Our institute is indebted to Professor Amitabh Ghosh for his consistent mentoring in the process of transformation of our academic infrastructure towards advanced manufacturing. In fact, this 5 days course has been conceived and configured under his able guidance. I don't have enough words with me to express our gratitude to Shri Ajay Chaudhary, Padma Vibhushan. During a short spell of his chairmanship, his inspiration has transformed the mindset of Institute towards manufacturing education. We are tremendously encouraged by the presence of Dr. Omkar Rai, Director General, Software Technological Park of India, for being among us today. In our effort towards convergence of core mechanical science with emerging trends of computer information technology, your guidance will certainly provide us encouragement and confidence. We are truly grateful to Shri Shyam H. Arjun Vatkar sir, our Chairman BOG, NIFT. His vision towards bridging the gap between the contemporary and emerging manufacturing technology through efficient backward-forward linkage has always been supportive in our endeavor. We are thankful to our director, sir, Professor P.P. Chattopadhyay, for his guidance and support. His vision is a motivating force behind us to pursue the area of excellence. We are thankful to all the dignitaries, speakers in different sessions of the short-term courses, representatives from industries, participants, and representatives of press and media for being with us. This is indeed encouragement in our endeavor. Now, with this, after this session, inaugural session, we will have lecture from Professor Amitabh Ghosh, and for that we will take a 5-minute break, and after that we will have a lecture from Amitabh Ghosh sir regarding the overview of manufacturing. So I request all the participants to be present after 5-minute break. Thank you.
Thank you.
So we conclude our inaugural session and we will move to 5 days course. On behalf of NIF fraternity and manufacturing fraternity as a whole, I convey my heartiest thanks to all of you. Thank you very much.
দেখতে পাচ্ছ স্ক্রিনটা? আচ্ছা, কথা শুনতে পাচ্ছ তো? মানে এতে যদি বলি, শুনতে পাচ্ছ? হ্যালো? হ্যাঁ, খুব ভালো হয়েছে তো, ভেরি গুড। হ্যাঁ হ্যাঁ হ্যাঁ, বুঝেছি। হ্যাঁ, বুঝতে পেরেছি। আচ্ছা, তুমি আমাকে এখন কথাগুলো শুনতে পাচ্ছ কিনা আমাকে একটু জানাবে। হ্যাঁ, আমি এখন, না না, এটা তো ফোনে বলছি। হ্যাঁ, শুনতে পাচ্ছ? পেলে শুনতে? হ্যালো?
স্যার, আপনি আমার কথা শুনতে পাচ্ছেন?
হ্যাঁ, পাচ্ছি।
আপনার কথা শুনতে পাচ্ছি না।
কেন? আমার তো মাইক্রোফোন তো আনমিউট করা আছে।
হ্যাঁ, পাওয়া যাচ্ছে, আপনার কথা শোনা যাচ্ছে স্যার।
আচ্ছা, ঠিক আছে তাহলে।
স্যার,
হ্যাঁ।
আপনার কথা পরিষ্কার শোনা যাচ্ছে।
So when do we start? Let me know.
At 5 o'clock.
5:10 we can start.
ও আচ্ছা, এখন 5:07. I think we can start, sir.
Okay. Thank you. So again, a very hearty welcome to all dear participants of this 5-day course. So the first talk is going to be presented by me. You can see this slide. Since I have been teaching for more than 55 years, I have understood one thing, that any program, later it may go to very difficult things, but it must be started with some soft lecture. So that in that sense, it will be a very soft lecture, discussing primarily the generalities. As you can see, the title of the talk is Whether Manufacturing. Now, it is not a spelling mistake. Whether is a very old English word, meaning where to, the destination. So therefore, this talk is going to be present some ideas about that which direction manufacturing is going and what we should do to be prepared for that. With this introduction, what I can start with, since I know that in these online programs sometimes voices are not clearly heard, etc. I have used extensive writing so that the participants can see what I am saying. Now, I think manufacturing is one of the important activities in the history of human civilization, converting natural resources to useful tools and products has been one of the primary factors in the progress of civilization. Since the Paleolithic era, man has been engaged in this activity. You can see here that these are the Paleolithic tools which the Paleolithic people used to form using the available stone pieces. Later, in the Neolithic era, or even much later, Mesolithic era also, you can see that they could also make weapons and tools, etc. like this. Now, this is a point which I have mentioned briefly, but I think I should also mention more elaborate way, that manufacturing is the driving force behind the world economy. You know that long back, 300 years back or 400 years back, everybody in Europe they used to think of coming to India. Now every Indian boy is thinking of going to USA and Europe. Now, this is something which changed. Why it changed? Because something happened through which manufacturing, they took a lead west and we were in the we fell behind. That manufacturing is closely linked to the growth of world economy. And the following slides show the two major changes in the world economy in the history of civilization. Now, such events which trigger a change in shape of the economy growth rate are termed as industrial revolution. And two such major revolutions have been recorded. The first industrial revolution and which happened with the advent of the first prime movers like steam engine. And the second industrial revolution, it happened with the emergence of microelectronics and the computer technology. Now, I think the progress of civilization is a very complex issue. How to define it by one parameter? So the most dependable parameter which you can take is the quantity, the E be the magnitude of the economy. So let us consider that, like the gross product, something like that. If E be the magnitude of the economy at some instant of time, then we know that the rate of change or rate of growth of the economy is proportional to the existing level of economy. That is, dE dt is proportional to E. Now, for a particular state of concurrent technology, and this growth rate, this proportionality will depend what kind of technology we have. Now, with a particular technology level, the above proportionality will be replaced by equality with lambda as the constant of proportionality, like this. So thus we get dE dt is equal to lambda E. Lambda is dependent on the technology or the available technology. So for a particular technological era, E0 as the initial value of the economy or magnitude of the economy, one gets the growth equation for the economy as follows. It is a very simple differential equation. Even school level, you can solve it and you get the solution as E is equal to E0 into E to the power lambda t. Or when you take the log on both sides, you get log E is equal to log E0 plus lambda t. Now log E0 is a constant. So if you plot log E versus t, that means a semi-log curve, you get something like this, a straight line. Because log E is proportional to t. It's a straight line. Now, what happens? The slope, as I mentioned, the slope depends on the technology. What is the level of technology? If there is a sudden change in technology, what happens? You can see that the growth rate changes. So this change in lambda or this growth rate, that happens in a short period of time, something like this. And something happened here, which is called industrial revolution. So log E versus t, if we plot, the straight line will suddenly change slope. And this industrial revolution happened twice. Or you can say, some people say thrice. So we'll just see how it happened. Now, once it happened when these steam engines were first invented. You can see around at the end of 18th century, you know, this was the yearly pig iron production in England. It was growing in the log like this. Now then, not semi-log. And then suddenly here, the whole thing changed because of the advent of prime movers. And this is the first industrial revolution which the mankind has experienced. And since that time, we have started becoming a developing nation, and the European and American and the European nations became a developed nation. So now I think another time we had a similar thing. Now you can see this is the gross domestic Western Europe has been plotted against time. You can see up to 1700, 1800, it was more or less this slope. Then the first industrial change. In between, there is a small change in slope here. This was because of the emergence of the internal combustion engines, which many people call as second industrial revolution. But in a major way, if you see that actually real change came around the end of, or not end of, towards the end of the 20th century, around 1970 or so, which is the second industrial revolution. And this happened in our lifetime. It is mainly because of the first industrial revolution happened with the development of the first prime mover, that is the steam engine. However, it should be understood that the direct connection of manufacturing with this event. Now, why we are doing this in our manufacturing lecture? Is there any connection of manufacturing with the first industrial revolution? This point may not be that well known amongst our students. So I think I would like to just mention it quickly. Now you see, it was the development of the boring technology with improved accuracy made the James Watt version of Newcomen engine with condenser to function. All attempts to run such an engine, although James Watt patent 10 years back, all the attempts failed. Till Wilkinson developed the manufacturing technology to produce accurate cylinder and piston. Now, this improvement in manufacturing technology made interchangeable manufacturing and mass production possible, which fueled the industrial revolution because that could make the industrial products within the capacity of common man. That means it invaded our domestic components. It was not only in the industry. That is a very major change. So it was the manufacturing technology which made the steam engine possible. Before that, you will see it was not possible. So Wilkinson's new boring machine, for which the James Watt had to wait for 2 years, and 2 companies broke because his model was not running. Only after this it happened. Now you see, in April 70, I will just tell what they say, this manufacturing, how it is related to first industrial revolution. 1775 April, Wilkinson delivered a cylinder with Bolton's language. Bolton was the financier of James Watt to make his engine. It does not air the thickness of an old shilling at any part. Wilkinson improved his technique in Watt's own language, inverted comma, a 72-inch cylinder being not farther from absolute truth than the thickness of a new sixpence in the worst part. And you see, you will now laugh at this definition of accuracy. The thickness of a coin may be a monstrous error by today's technology, but that helped the engine to run. So the second industrial revolution happened during the 1970s and 80s. It happened in most of our lifetime, and we have experienced it, of the last century when microelectronics and computer technology developed.
Yeah.
In this case also, manufacturing technology.
Excuse me, sir. It seems your speaker is on, maybe because we are.
Hello?
Yeah. Yeah, Professor Amitabh Ghosh, sir.
Yes. Should I proceed?
No, we can listen. Ghosh, we can listen comfortably.
Huh?
Yes, sir. Okay. You can listen. The 2 voices are coming actually.
Somebody, you have to mute all others. You have to mute all others.
No, not I am going to interact now because this is a online lecture and here it will be difficult to interact at this stage. Kindly keep your questions ready and pass it on to the organizers. I will answer to them. In this case also, manufacturing technology also was the driving seat. As this industrial revolution's prime agent was micro-manufacturing technology that made the very large-scale integration possible. The primary help came from the photolithography-based micro-manufacturing or micro-machining, and that has the current capability of the fabricating feature sizes smaller than a small fraction of a micron. That means we have gone to deep submicron level fabrication. However, this technology can only help in two-dimensional miniaturization of a device, and the basic purpose of such miniaturized device is to manipulate information. That was the primary aim of the second industrial revolution. Now, I think it is now felt by many experts that we had 2 major industrial revolutions. Will there be another one? Now, it is felt by many experts that the world is going to experience the third industrial revolution in not too distant future. And that also will happen with the help of advanced and new futuristic manufacturing technologies. The third industrial revolution will also make entry predominantly through advanced manufacturing technology that can produce miniaturized devices. Now it is not only two-dimensional miniaturization, it will be three-dimensional miniaturization, which will make the machines and devices miniaturized. So the objective will be to manipulate not just information, but to actually manipulate material and the functions of the devices. That will be miniaturized. And this amply makes it clear how the advancement of fabrication technology is linked with the progress in human civilization. It is not very clear, the connection is not very clear, but a little deeper study shows us that manufacturing is the key player in this industrial revolution. It is thus important to have at least some idea about such advancement so that the country, our country, can develop the right kind of new technological manpower and play a center stage role when the third industrial revolution knocks at our door. In the previous two cases, first case we completely missed, second industrial revolution also missed, but we became only the user or a follower. But we should not happen that to happen in the third industrial revolution. We should be also at the center stage. With this introductory note, a brief discussion of the advances in manufacturing technology and the futuristic issues can be taken up. So far, I have discussed just the background of why we should consider manufacturing or manufacturing technology an important point and what we should discuss. So that's why we are saying that the trend of development, what will be in the future, is very important for us to see. So now what I will present, a general discussion on manufacturing processes. This being an introductory lecture, I will present the whole issue of manufacturing processes. Now, this session will be presenting now an overview of the various facets of manufacturing activity and to have a glimpse into the future possibilities. Now, some major classification can help to understand this activity before the special topics are taken up for discussion, and also the subsequent lectures by the leaders in their specific fields, and special issues and special topics will be presented in the next 4 days. Having an overall view can also help us in conceiving new directions once the current trends are noted. Now, manufacturing involves not only the processes, as it has been mentioned by the Honorable Chairman of the Board of Governors. It is not only the processes, but there are so many things, material handling, then management, marketing, everything is in manufacturing. But I think in this particular short course, we will emphasize the processes, because the machines, tools, and organizations which act as the vehicle for all activities, our manufacturing processes play the main role. So this session is devoted to a discussion on the processes. So an overview of the manufacturing processes. So first we will divide or classify all manufacturing processes into two basic classes. You are all familiar, there is nothing new in this. One type of manufacturing we call bulk processes, which is material transformation and bulk handling, raw materials, these, that, ores, all kinds of things, chemical industries. And the others are called unit processes, where we produce individual pieces. Here it is again material transformation plus manipulation. So you can see the primary difference is one is bulk handling, other is individual manipulation. Now after this I think we should concentrate more on the unit processes in this session. So unit processes are what? It is material transformation and manipulation to impart the desired shape, size, quality, and finish to our product. It will require what? Manipulation and control the fabrication processes, and then it will go to testing and inspection, and finally marketing, etc. And whole thing is called manufacturing. And therefore, the different components of a manufacturing activity can be generally expressed in this diagram. It is manufacturing, it has inputs are what? One is raw material, as you can see. Raw material is one input. Then energy, it requires energy to change these things. Then information is another input. What shape, what size, what finish, etc. So all these inputs, and through this manufacturing activity produces the product. So this is the diagrammatic representation of a general manufacturing process. So now when considering manufacturing processes, this can again be classified into two major groups, depending on the basic approach for shape generation as indicated below. This particular point may not be known to all, but it is a very important thing if you have to discuss futuristic issues. Now, this classification are called one set of manufacturing processes follow a top-down approach, another set follows the bottom-up approach. What are these? Now, top-down approach is where we take a particular piece of metal, where shaping of the material to achieving required shape, size, accuracy, finish, and properties, and a very large number of machines, types, and many methods of shaping have been developed. So these are what? These are the pins, you all know, this is starting from the stone edge tools. You take a piece of stone and remove the excess part, and you give the required shape so that it becomes a tool. Now, same thing we are doing now, though in a very different scale, these VLSI chips. Now, fundamentally, the process is same. That means you take a piece of metal or material and you give the shape to that, either by removing the excess material, we call machining, or by compressing it, giving a form, we call forging, or melt it and put it in a particular kind of mold to give the shape, casting. Whereas in VLSI chips also it is the same thing. Here you are giving the shape by removing the excess material, of course in a very deep submicron level through photolithography. But basically the approach is same, and these are all top-down manufacturing processes. For your information, all the majority of the processes like turning, all the machining operations, your forming operations, sheet forming, all these are actually basically top-down manufacturing processes. One very interesting example in India we have, a unique example of top-down manufacturing is this. I think many of you have visited this. You can recognize this. This is the Kailash temple in Ellora. Now you see, it is something, it is unbelievable. You can see these are human beings. So you can realize that what is the size of this. It is almost equivalent to a 10-story high building. And everything, all small figurines, windows, doors, all curtains, everything, all the whole complex. And you can see there inside you have the houses for shramanas and others and all. That it is not, it's an extremely complicated and huge complex, equivalent to a 10-story building complex. And the whole thing was produced by cutting down a single piece of stone. And this is called top-down approach. Of course, a very peculiar example, but I think it is something, so far as India is concerned, very unique. Now, in case of bottom-up approach, the situation is very different. Here, the required shape, size, etc. are produced by adding material gradually. So therefore, how it happens in a particular, the first bottom-up approach procedures where these are, they used to be called in those days rapid prototyping. Now, of course, they are called generative manufacturing. First, a CAD model is produced. Then this CAD model is computationally sliced, making each layer a thin layer of required shape and size. And finally, these are actually generated. There are various methods of generating. I will not discuss that. So stereolithography was the first thing which was done using laser beams. Now this way you, one by one, you generate and you get the final shape. This is the first, the STL method, stereolithography method, which we had. Now, of course, there are many other methods. Now, this is a completely different approach. You don't take a piece of metal and produce the right shape. Here you add materials in small quantities, either in the form of a plane or in the form of a point, all are possible, or in the form of a line. Now, one example, again, famous example of bottom-up approach is the pyramids. You know very well how pyramids are formed. The small pieces, billions of such small pieces of stone were added to make this huge structure, which is almost 50 or 60-story high building. So therefore, we can divide the manufacturing processes into two different groups. One is bottom-up, other is top-down approach. The old processes which we have been using so far are actually top-down, except in some few cases. But in future, you will find bottom-up approach is going to play a very major role in our system. Now, with the progress of science and technology, newer horizons are opening up, increasing the process capabilities of various top-down and bottom-up manufacturing processes. Now, initially, top-down process used to make things of big size or macroscopic size or mesoscopic size, maybe some meters to millimeters to at the centimeters and so on. Bottom-up approach, similarly, they used to start from molecular level, the chemical processes. But now with technology, they are also gradually increasing in the size. So the progress is making top-down to approach smaller sizes, and bottom-up capability, bottom-up manufacturing capabilities going up at higher level. So therefore, you can see that how I show you is this. The top-down started at the 1950s. They are mostly macroscopic or mesoscopic, and bottom-up approach are mostly at molecular level, chemical processes. Now we are making smaller and smaller thing with top-down approaches, and we are making now bigger and larger sizes or feature sizes with the bottom-up approach. So this is how the progress are making. Now, so far as the bottom-up approach is concerned, the real future lies with the self-assembly of material. What is meant by self-assembly of material? Now, where the material assembled by itself without the intervention of an outside agent. I'll see why it is so. The size capability of the bottom-up process also, as I just shown, that it is increasing, and gradually they are coming to engineering field rather than chemistry. So manufacturing processes dictates the characteristics of other components, the machines, tools, inspection and metrology, assembly and automation. The rest of the presentation will be today devoted to the discussion of manufacturing processes only. So now we'll have a discussion on manufacturing processes. What are the general whole scenario and the whole family of manufacturing processes, the types and classification? We will attempt that now. Now, the classification, the more detailed classification of the existing manufacturing processes can be understood by considering the following basic aspects. One is what type of energy is being used for a process, or what is the mechanics of material removal involved, or what is the energy source we are utilizing, or what kind of manipulation and control. So these are the points we should keep, and on the basis of this, we can classify the existing manufacturing processes. So now, so therefore, if you see the energy type, now you have mechanical type energy, electrochemical energy, chemical energy, thermal energy. You can all recognize that various manufacturing processes we have today, they are basically the energy types can be classified. Like mechanical is the pure machining processes. And electrochemical is your electrochemical machining, etc., chemical milling, etc. Chemical is the chemical milling. Thermal is your various types of thermal processes like laser-based processes where you use the thermal energy or welding, etc. Similarly, when you go to the mechanics of material removal, you can see plastic shear, erosion, ion displacement, corrosive reaction, fusion and vaporization. Again, these are all familiar to you because plastic shear or deformation is the machining, erosion is your abrasive jet, abrasive machining processes, ultrasonic machining, ion displacement is your ion beam machining and so on. Corrosive reaction is your chemical milling, fusion and vaporization is laser-based processes where you can drill holes or cut materials. Energy source. Now this was energy type. Now you should also pay attention to what kind of energy source you have. It can be mechanical motion, most of the typical machine tools. Mechanical and fluid motion, like your abrasive jet motion, etc. Electric current, like your ECM. Corrosive agent is chemical. Electric spark machine, EDM, etc. That's a thermal process. High-speed electrons, that is electron beam machining, and powerful radiation, that is laser-based processes. So this way we can also have a closer look into the various types of manufacturing processes to have an overall understanding of manufacturing. The overview of the manufacturing processes, we can again classify them into two groups, top-down, which is represented by the white, and bottom-up, which is represented by green. Now, bottom-up is the addition, or what we call these days additive manufacturing, which is there is no tool or nothing, whereas top-down is taking a material piece and giving the required shape. Now, the manufacturing processes for shaping are material conservation process, where you maintain the amount of material you take and give the shape to the same volume of material, which you can see is casting, forming, and powder metallurgy. Material removal processes, where you remove the excess piece of material to give the required shape and size. It is the conventional machining, unconventional machining, and micro machining. And unconventional machining can be again mechanical, electrochemical, chemical, and electrothermal. And in the bottom-up group, you get material addition processes, which is called additive manufacturing. There you have two types. Primarily, one is the present-day rapid prototyping processes like LOM, SDC, STL, FDM, that is fuel deposition modeling, SLS, selective laser sintering, and so on. Some more new processes are also coming. And the other group, which I will also discuss, because this is going to be the real future, is self-assembly. So thus, we can again, classify our manufacturing process, whole family, in this way. Now, I think let us see what paradigm shift in manufacturing can be expected in the near future. That is our main point of discussion. Because that is what I mentioned initially, that we should be careful and we should plan our curricula and our program so that at least some exposure to these things are given to our students, so that when they go to their real working field, they are not completely taken aback and they are taken off the guard. A quick glance over some major characteristics can help us in identifying such expected changes in the next few slides. This will be attempted, and let us see. Beside handling materials with very low machinability, the progress in manufacturing science and technology is aimed at. These are the four objectives to which the manufacturing will aim at. Number one, higher accuracy and finish, producing complex geometrical shapes, generating extremely small features and microfabrication, and achieving artificial intelligence. Ultimately, we are driving towards artificial intelligence, as I will show gradually in my presentation. And the next slide shows the trend of engineering symbolically. I have prepared a diagram which in a composite manner will show you that which direction our technology is progressing. And obviously, if the technology is progressing in direction, our manufacturing processes, etc., should be also matching that and should be also aimed at achieving that kind of trend. Now you see this diagram is an interesting diagram. The horizontal axis is 1 by size. Why 1 by size? That if size becomes small and small, 1 by size becomes larger and larger. It goes like this. Other axis is degree of automation and intelligence contained in the device. More and more intelligent and autonomous it becomes, we go along this direction. So here you can see currently we have the CNC machining centers. Certain degree of intelligence it has. Size-wise, it is pretty big. So it is 1 by size is small. Then you go to micro machine tools. Size of these devices are small. And gradually we are going towards much smaller machines, and we are going to imitate the nature, which are nothing but the molecular motors. You see, all these protein motors are continuously functioning in our bodies. We are not aware of. It's a very interesting thing. Those who are familiar with bioscience, they are definitely aware of this ATP synthase and such things. And I'll discuss about it a little bit later. The other development is now say Mars Land Rover. It is quite autonomous and intelligent because, you know, suppose when it is moving and it faces some crevasse, immediately it should decide that what should be done, that a brake should be applied. It cannot send that image to Earth station and wait for the guidance or command that you stop, etc. Because by the time it comes, few minutes have passed and the damage has been done. And the futuristic autonomous humanoid robots which we are aiming at, now they are actually part and parcel of science fictions, but you never know what will happen in another few decades' time. The other thing development is that they are becoming simultaneously small and also intelligent. Now this diagram shows that, you know, these are micro robots which have been injected inside our veins, and they are manipulating some sick blood cells, you know. So therefore, this is the kind of aim and objective of the technology and manufacturing. So therefore, this is something which has to be kept in mind. Whatever is necessary, that has to be done through our. Now, one thing is important which I mentioned, miniaturization. Now, miniaturization and achieving intelligence are the two major goals of the current developments in engineering. As will be shown later, these two are interrelated. I'll show you. Thus, it is very important to have a discussion on miniaturization and micro manufacturing. Why miniaturize and why we do this, that is very important. And the growth in microsystem technology and economy, that means why it is becoming more and more popular. You can see the economy based on MEMS economy, that's micro electromechanical system. It is growing an exponential rate. Why it is so? Because its importance has been realized and it is growing like that. Now this I have to take a few minutes of your time to explain. Now we have seen that the second industrial revolution was based upon two-dimensional miniaturization of computational systems with an objective to manipulate information. That means now we have these computer chips which are very small, like even a centimeter by centimeter chip can contain 1 million transistors, you know, interrelated, interconnected. These are called VLSI chips. That's why your mobile phone is functioning, because it has VLSI chip. Earlier, computer in the IIT Kanpur used to be a very tourist attraction place. It's a huge building and full of huge machines. The tips are moving, lights are blinking. Whenever some guests or family members used to visit us in Kanpur IIT, we used to take them to our computer center, and they used to see that with wide eyes. Oh, this is computer. The whole building was completely full by one computer system. Now, the power of your smartphone is more than that. Why it has become possible? Because you have miniaturized. You have been successful in achieving the same amount of computational power within a very small space. Like say, for example, few decades back, or two decades back, or 3 decades back, we used to get this pen drive. It just started coming. When the computer systems were first emerging, then the cost of a memory, one bit used to cost $1. Gradually, you see that it started decreasing. Now, the pen drive you have in your pocket when you are going somewhere to make your presentation, maybe it is a, you can say 64 GB or something. That means that 64 GB pen drive should have costed $64 billion. But now you have to pay only perhaps a couple of hundred rupees to get it. That's how miniaturization is helping the technology and technology to actually influence our society. Otherwise, for example, the size is not that very important. Cost is very important. For example, the main processor chip in your laptop, it was 100 times more in size, maybe from 1 square centimeter to 100 square centimeter. It could be easily fitted in your laptop and the whole thing should have been the same. But if the cost of that chip is 100 times more, your laptop will cost how much? 20,000 into 100. That is 20 lakhs. You will not be able to purchase one. So that's why the cost is also very important, so that the reduction of the cost is very important, and miniaturization is one group to that. As I mentioned, that the third industrial revolution will be characterized by three-dimensional miniaturization. Earlier, we are making only computer, the electronic circuits miniaturized. That means it is a two-dimensional miniaturization. But now, you will miniaturize the whole machine. Like a robot, you will miniaturize it to micron level so that it can be injected inside your brain for a particular type of task. So this is going to be the real issue in the future which we will be facing. So now I think I will devote some time to discussion on miniaturization and microfabrication, because that will be a major objective of our futuristic manufacturing processes. Now I think, as I mentioned once, but again now let us come back to that. Why miniaturize? Now, the capability enhancement through large-scale integration, which I have mentioned, economic reasons, which I also have elaborated, that miniaturization can make things cheaper and you can afford it, and accomplishment of special high precision tasks and approaching intelligence. Now you see, if you want to make an intelligent robot, you will need, suppose it's robotic hands. Nowadays, we put few strain gauges in its 3 fingers and we expect the hand to be an intelligent hand. It is nothing like that. For a hand to develop the capability to have a tactile image formation ability, that is when your hand, you grasp something, you form a tactile image so that you can feel what it is. But I think that requires what? You have thousands of sensors in your palm. Similarly, so therefore, intelligence will require huge amount of sensory information. And that means what? Huge number of sensors to be packed in a very small area. So how can you put few thousand sensors in just few square centimeter area unless you miniaturize it? And intelligence can be achieved only when you have huge amount of information. And that means huge amount of sensory devices. And that will be possible only if you make them miniaturized and pack them in a small area. So therefore, intelligence, what we are talking so much about, cannot be achieved unless you go for miniaturization. And few other things which I have already mentioned. Now, how our miniaturization technology is progressing? What is the trend? Now let us see the trend. So when we start here, this is the level of material manipulation, and this is with time. Then how much material we can manipulate, that what kind of miniaturization is possible, and this is the years how it is progressing. So now you see, macroscopic scale, it was the traditional processes, level of material manipulation was macroscopy. And then when you go to micro, our current micro and RP technology, rapid prototyping technology, then you come, this is around 2000. Then you go to nano level, which we are now talking so much about, nanotechnology, etc. Material manipulation is at nano level. Nano level means you understand the fraction of or 10 angstroms is 1 nanometer, I believe. So when you go to manipulation of that level, we call it nanotechnology, and which you are now more or less capable of handling. We call it nanotechnology. And now I think we are going towards atomic level. So our ultimate goal is that we should be able to manipulate material atom by atom or atomic level. That, of course, we have still not achieved, but we are going to achieve it very soon, as it appears from the trend. And what are the technologies for these things? That also you can see the range of current microfabrication technology. We have some microfabrication technology. Conventional machining is in millimeter level. 200 micron level it can go to. Then micro drilling, grooving, etc. It goes to 100 micron level. Then we have optical lithography, which you are familiar with, which can go to micron level and submicron level, 100 nanometer, 10 nanometer, so on. This is all you can achieve by optical lithography. Then diamond surface micro machining can go to nano level, which is in a restricted sense, you can go to like this. Then we go to X-ray lithography, which has a range of micron to angstrom, X-ray lithography. And finally, we go to deposition technology, with which you can go to atomic level. So these are the current microfabrication technologies of various types, of course, with their different range capabilities, size range capabilities. And what are the processes? Again, the whole family of micromanufacturing processes can be divided into two groups, as I mentioned earlier. One is top-down, and the green one is bottom-up. So this is the conventional machining processes with higher precision, mechanical processes like diamond micro machining, ultrasonic machining, thermal processes, micro-ADM, beam type processes like laser beam machining, electron beam machining, then sputtering techniques like ion beam machining, then lithographic processes like bulk etching processes, polysilicon technology, Wards technology. These have developed primarily because of the need of the microelectronic industry, the Liga processes and surface etching processes. These are all top-down currently available micro-manufacturing processes. The generative processes or bottom-up approaches are microsetting by material addition process, FIB technique. FIB is focused ion beam, which can take you to tens of nanometers. Self-assembling techniques for shape generation. Self-generation can be two types, uncoded self-assembly, other is coded self-assembly. Uncoded self-assembly means what? That the primary element, that is the brick with which building block, it is uncoded. It will just self-assemble, just minimizing the energy. And the coded self-assembly means its different sides will have different characteristics, and so the final shape which it will aim at will be a definite structure. This is the real ultimate aim which we should go for. Now, the next slide will show you that what are the major changes in the engineering activities. Now, this includes the changes in the design concepts, information flow during fabrication, level of intelligence during operation, and the energy currency involved. So in design, what are the changes what is the current trend of change in the design? from currently we have machines and devices which have many components. But when you go to micro and nano level, the machines and devices will be monolithic. You cannot have a micron level mechanism or device in different components and assemble them. So therefore, what will happen? The all micro-sized machines and devices will be one piece, but they will have the capability to have relative motion, etc. But that's a different issue. We will not go into that now. Second, what will be the change in design concept is miniaturization, which I have been emphasizing. Next will be massive parallelism. This is a point, or this is a word I should explain. What is massive parallelism? Now you see, anything like you will find that if you just check any muscle of any animal or even your own muscle, you will find it is a combination, a bundle of huge number of micro thin threads or proteins. Why it is so? Why not it is one thick block of protein? Now this massive parallelism makes two things. One is when you want to have information, just one piece of information will not make it intelligent. You must have hundreds, thousands, millions even sometimes, and it must feed the whole system in a parallel way, simultaneously. That is one aspect of massive parallelism. Other is that when you make a thing very small, then some scaling laws will produce some advantages which you should be able to take. Like our muscles. You know, if you make one block of protein, the kind of force it will be generating, if you make hundreds of thousands of fine threads and bundle them together, each thread is produced acting simultaneously, that muscle will produce 1,000 times more force because of some scaling effects and scaling laws. Now, therefore, massive parallelism and miniaturization is an absolute necessity for futuristic machines. Now, again, you will find the materials which you will have in future will be soft. You see, all natural things like yourself, all naturally developed objects, they're soft, not like steel or something. Because they are all formed by self-assembly. And self-assembly will be possible only when their attachment is not very strong. Each individual building block, I will show it later. So therefore, ultimate characteristic will be the whole material will be little bit soft, not as hard as a metal is. In fabrication, the trend will be bottom-up approach, self-assembly of materials at micro level, nano level, and molecular level. And in fabrication, sometimes in future, we will have self-replicating systems. That's like living objects. We are going in that. Actually, NASA has some such projects which may not be known because these are very highly classified projects. For colonization of other planets, you need self-replicating modules. In operation, the devices will be intelligent, self-learning, which some of the electronic circuits and current day have already achieved this, and even self-correcting. That means nowadays when you type something, if somewhere a comma is typed in place of full stop, the program doesn't work. But I think in future, it will understand that this is a mistake and it will be able to make that correction. So in operation, it will go to intelligent, self-learning and self-correcting operation. And energy, a major change will come that when you will be using biochemical energy, like metabolism, photosynthesis, in many cases, you will find that coming futuristic industries after half a century have many machines which will run on photosynthesis using solar energy. So therefore, what we have seen, the top-down approach for shape generation at the micro level is restricted to two-dimensional or quasi-two-dimensional features, but producing three-dimensional objects and devices by machining is not possible except for some very simple cases. How do you make three-dimensional objects except for some very small places? So for this, you will find that we have to imitate nature. Consider yourself. You grew in your mother's womb from one cell to now a few trillion cells. In so much such a complex shape, such complex system, how it has happened. Nobody has done from outside, nobody has taken one piece of protein to another piece of protein. It has all naturally self-assembled, self-generation system by a bottom-up approach. Now, nowadays, as you know, engineers are taking a lot of lessons from the nature, because nature is the best teacher. It has been now more or less people are convinced. So in every aspect of engineering, people are trying, whether it is in design, whether it is operation, or whether it is fabrication, we are trying to imitate nature. So it is now more or less sure that to get the third industrial revolution realized, we have to depend on bottom-up approach. That means where shapes will be generated, very complex shapes, multi-material shapes will be generated by a bottom-up approach, adding material in small elements, small building blocks to generate a huge structure. But it has a difficulty. The bottom-up approach involves enormous number of manipulation of material elements. Suppose a regular cube with 1 micron side, shown here. This is a cube, 1 micron, 1 micron, 1 micron. Now it will consist 10 raised to 9 molecules, 10 raised to 9 molecules. Now if one takes a millisecond for each manipulation, that means 1 molecule at a time, the time to assemble this 1 micron by 1 micron by 1 micron cube will take 10 raised to 9 seconds, or about 32 years. But you are such a big, anybody, say like 4 of us, our dimensions are meters. How you are growing in a time frame of 9 months only? Now this is impossible unless you go for major change, that is self-assembly. That means material will be assembling itself without the intervention of somebody from outside. Therefore, the only practical solution is through self-assembly of material, as happens in nature. So in this, what is going to happen? The information on the material manipulation for current manufacturing process is from outside, like say for a program or some kind of tool, or sometimes it is a drawing in a drawing board in the old times. So thus it's a severe limitation. Thus you must achieve shape generation by self-assembly of material without any intervention from outside the process. It should be self-assembly. All information regarding shape, size, etc. should be contained within the process itself. So therefore, most important thing, or major revolutionary change in manufacturing is going to come. It may not be now immediately, but in future, the self-assembly of material. It's a paradigm shift in fabrication technology. But remember, not that everything will be assembled in a self-assembly way. Like a locomotive engine will not be self-assembled, but this will be a very decided, like say for example now, VLSI is not being necessary for your locomotive engine or an aeroplane, but it is having extreme important role to play in even the macroscopic size, things which are produced conventionally. So self-assembly of material will be necessary not only to make the micro-sized devices in future, but even for macro-sized objects. Now, what is self-assembly and self-generation? Now, self-assembly is coordinated action of independent entities under distributed, that is non-central control, to produce a larger structure or to achieve a desired group of effects. Now, self-assembly or self-generation is a process in which components, either separate or linked, spontaneously form ordered aggregates. It can occur with elements having sizes from molecular to macroscopic sizes even. Now, as I mentioned earlier once, the self-assembly or manufacturing by self-assembly can be of two types. One is uncoded self-assembly, which happens, which I'll show you just in the next few slides, minimization of potential energy. Why it will assemble? Because that assembly will cause the total energy to become lower and lower, and in the natural process will always aim at lowering the energy. Whereas coded self-assembly, there will be instructions about the shape and the way it should assemble, which is a more complicated thing. They call it either coded self-assembly or program called self-assembly. Like we all have generated, I have not become a goat, I have not become a tree, I have become a human being of a definite type, only because in the DNA, all the information is coded, and that helps the self-assembly to give a definite direction. So basic requirements for self-assembly and generation need will be some. Components and elements should be groups of molecules or segments of a macromolecule that interact with one another. They may be same or different. Their interaction leads from less ordered state to more ordered state. I'll show some example later. Interaction will be components need to interact. Definitely they must come together. And the interaction can often be selected and tailored by definite shape, and particularly in case of mesoscopic or macroscopic objects. Reversibility or adjustability. That is, when two components come together, they should be able to adjust positions once in contact so that the minimization of energy is possible. Environment, self-assembly normally takes place in a solution or at an interface which allows the required motions of components. They are generally in a liquid and they have thermal agitation. And mobility will be due to the components need to be mobile so that they can come together. Equilibration. Equilibration is, equilibrium is required to reach the ordered structure. Now these are the, now at the root of self-assembly process lies the minimization of surface energy. The current available self-assembly processes depend on the surface characteristics of the basic elements. Primarily, two types of surfaces are engineered now. One type being called hydrophilic, that means which love water or which prefer contact with water. The other type of surfaces are called hydrophobic, that means they avoid water. These surfactants, etc., you maybe the chemical engineers are very familiar with these things. So the assembly always attempts to minimize the area of the hydrophobic surfaces in contact with water. So when you put a large number of elements in water and they have hydrophobic surfaces, there will be natural tendency for them to come together so that ultimately the total exposed surface area to water or in contact with water is minimum. So the next slide will show a very simple elementary example, but that will tell you that how it happens. Say a component that interact irreversibly, that means once they come and they get attached, they cannot adjust. So they produce disordered products. Say like this is a basic element, another one comes and touches it and gets attached. Another one comes and gets attached. So this way you generate a disordered thing. But however, when they can adjust position, that's why I said that ultimately all such material finally will be soft material, because their attachment will be not that firm. Then they can adjust and they can minimize the energy like this. Suppose this is the basic element, another element comes, they get attached, but then total area here is more, so it will minimize the area. How it does? It will minimize the total area in contact. So this way another one comes, this way, and finally. So a ordered structure, a definite shape. Long back, I was in Kanpur, one of my students was working on this through simulation, of course. And interestingly, I found I could generate a large number of shapes of different types of viruses. You will find, if you do by computer simulation, you will find the shapes you are generating are very similar to the commonly found viruses, including your coronavirus. Now, at the molecular level, you can see that the molecule we have, one side will be hydrophilic functional group, other side is hydrophobic carbon chain. So if you put large number of, say, millions of such molecules on water, they will automatically adjust their position in such a way that all the hydrophobic carbon chains will be away from the water and all the hydrophilic ends will come into the water. So you don't have to do anything. Even if there are billions of such molecules, it will take place this ordered state in a fraction of a second. It doesn't require any manipulation from outside. So when you put large number inside water, then what will happen? These molecules will adjust their position in such a manner that all the hydrophobic ends they are in contact and they hide from water being inside the whole thing. This is a bilayer. So in another kind of density, you can form mishal. That means there will be a spherical object where all the hydrophobic ends of these molecules are inside, avoiding any contact with the water. Similarly, so for example, this is the basic element where these surfaces are hydrophobic, red, hydrophobic. If you put them in water, what will happen? They will join in such a manner that the hydrophobic ends are coming in contact so that they are hiding their exposure to water, minimizing the surface energy. So this way, gradually, they will develop like this, producing an ordered object. Suppose if you change the shape slightly, a hexagonal basic element where alternate sides are hydrophobic and alternates are hydrophilic. If you put them, then what will happen? Automatically, the hydrophobic ends will come in contact, and the hydrophobic means that energy will be minimized. And another one, if you go this way. Whereas, if you put all the surfaces are hydrophobic, then the connections will gradually develop like that, so that minimizing the total surface area. Here it is a line, of course. The circumference will be minimum. So this way, by designing your basic element and their characteristics, you can produce a different kind of shape by self-assembly. You don't have to do anything. That's what nature does. But of course, in a far more complex way. And these are the other examples, like say, if you have the basic elements like this triangle, then they will not combine like, they will combine like this, not like this, because the total area exposed to surface will be more in this case. So if they are rectangular or say square, they will combine like this, not like this. Then this will be multi-stage. Multi-stage self-assembly means first you will produce a smaller objects, and these smaller sub-assemblies will they go to major assemblies, and finally the whole object is produced. So these are all binary surfactant systems. These are used in chemical nowadays, but mechanical engineers are gradually coming in this direction, and manufacturing is gradually becoming aware how to use this multi-stage self-assembly system to produce. But we are still far away from developing a machine. You know? These are the self-assembled materials. So many experts believe that the world is heading towards another industrial revolution, the third industrial revolution I have been telling so far. The primary indicators for this is the glimpse of a paradigm shift in science and technology, represented by frequent merger of engineering science with life science. Now I think our engineering and life science will have a lot of interaction. Actually, that's why long back, 20 years back in IIT Kharagpur, life science was made a compulsory core course at the first year level. Engineers must be familiar with life science, because in future, they will be facing many things which are actually dependent on the nature and life science. A new area of R&D has started raising its head, that is called synthetic biology. Synthetic biology means that the machines and devices developed by synthetic biology will be artificially made, but they will have many features and characteristics of living entities. The self-assembly offers a possible route to the fabrication of three-dimensional microstructures, machines, and number of problems in manufacturing, including problems in robotic assembly, may be eliminated by self-assembly. The next video clip shows through animation how nature self-assembles to develop living object, which has been shown in the self-assembly of the rotating tails, which helps in the locomotion of flagella bacteria. You all know flagella bacteria, they travel, and how their locomotion takes place with their tails, they rotate at a high speed. I'll show you a short video clip that will tell you the wonderful way the nature makes things. No, video is not working. So fundamental changes in the philosophy of designing the systems and devices of the new era are indicated in the next slide, as you will see. Now you see at present, material body, sensing devices, and the actuators, that means the material body, the sensors, and the actuators which cause the movements, they're all separate entities. But in future, you will find just like our living object, your actuators, your sensors, your body, they're all smeared into one body, one merged together, and material body with integrated and distributed sensing and actuation. That will be our future machines. Then there is a strong possibility that the energy source for functioning of a device will be biochemical, that is hydrolysis of adenosine triphosphate. It may be also possible that the distant future, many devices and systems will use photosynthesis as the source of energy, just like our trees. Thus, the sun will be the main source of energy, and the machines will produce oxygen instead of carbon dioxide. Can you imagine its impact on our world climate? Now, the picture below shows a biomotor that drives the tail of a flagella bacterium, and the driving force is developed by the flow of ions from the upper layer. Here is the ion concentration is higher, and lower it is lower. Here, all the motors and activities of our living objects, including your bodies, they're all through ion movement. That's why we have to be careful about our ion concentration. And dehydration is such a big problem, as you all know. So this is the ionic motor, this is the rotor, and this is the stator, and ion concentration, the hydrogen ions are flowing through this. And just like electricity, this causes this to rotate. And this one is called the ATP synthesis. Here, the motor is below one part, and that motor rotates, which I'll show you another one. Yes, the motor rotates, hydrogen ion flows. This causes the motor rotate sharp, and this is a forging machine. These are protein lobes. And what happens? The adenosine diphosphate, that means our ATP through hydrolysis is converted into ADP and phosphate, and also some free energy, which we use for all our activities. But this, we consume almost 25 kg of ATP every day. So you have to reproduce that ATP, and that is done, that is the ADP which comes out of this, and phosphate, they are again combined by these machines, which are called ATP synthase. So how it happens, as you can see, that this motor is rotating at every stage by 120 degrees, and this lobe, it is taking the, you can see the adenosine diphosphate and photon phosphorus, making adenosine triphosphate. It goes out. Again, it is used. So this machine is actually at the atomic level, it is just like a very sophisticated electrical motor, but here it all runs by electrostatic phenomena, because this is the ion movement, and that's why electrostatic phenomena is the real thing by which it happens. Now, the nature of the progress in manufacturing in the future is depicted in the next slide in a very similar. Now, this, of course, we have very high ambitions to imitate nature. It will take many, many, many decades where you can go somewhere near that. But the direction which you are going, as an engineer who will face the challenges of the future, in which direction we are going, can be represented by this composite diagram by me. Now, the traditional processes, we know that material exists independently of the shape. There is a material, and we have to give the shape to it. Next, it is generally all the components and the objects are of single material, like say copper, aluminum, or something like that. Next will be material addition or removal at the macroscopic or mesoscopic level, like most of the machining and other processes, where material addition or removal is taking place at macroscopic or mesoscopic level in the current present. A template or in a computer program, whatever it may be, but from outside the process. And assembly is an some objects which have different materials. And material addition at micro level, information is from outside. Still, that is one point. Information is contained in a computer program or something like that. And assembly can be eliminated in some limited cases. That means some sub-assemblies can be eliminated and you can produce something as a sub-assembly. Already we are producing through generative process objects where has relative movement possible. Multi-component devices, as you all know. Now the future generative process which we are aiming at, maybe another decade or so, shape and material grow simultaneously. Multi-materials objects will be very common. Material addition will be at the nano or molecular level. And information will be partially in the process, partially from outside. That means sub-assemblies will be inside material information, and the overall, when assembly will have to be done, it has to be from outside. And most often, sub-assembly will be eliminated. That will be by generative process. And final, ultimate self-generative process, where it will be a self-generative, self-controlled, lifelike biological growth. So the various disciplines of engineering and technology are also undergoing continuous transformations. The major science and technological institutions of India must also keep abreast with these changes and redesign the various curricula. Only then our country will be able to face the challenges of the impending third industrial revolution. And India will not be compelled to be a silent bystander. The progress of engineering disciplines is depicted in the following few slides in a symbolic fashion. Only with such progress can synthetic biology be achieved. Now you see the traditional, what the future engineering subjects will be. We have the current traditional engineering subjects. Physics will be main input, chemistry will be a main input, mathematics and computation for extensive simulation and modeling will be an extremely important part for futuristic engineering, and life science will be also an integral part of engineering. That will give our future engineering curricula of the new era. The basic nature of the futuristic engineering can be represented by the diagram shown here. What will be the nature of futuristic engineering? The primary component will be miniaturization will be one aspect. Massive parallelism will be another aspect to make things intelligent. Then bottom-up approach and fabrication and self-assembly mass manufacturing will be necessary. And embedded biochemical energy source and control electronics will be another very important. And overall, we will use smart materials. So a combination of all these things will be depicted, or is actually what we have to aim at in futuristic engineering. So any further discussion of the subject is, of course, beyond the scope of this presentation. It will be only a very bird's eye view of what we may expect or in which direction we are moving. In some times, maybe it will change a little bit, because you know, to forecast technology is very difficult. Even in the 80s, there was not even any science fiction, a thing like a mobile phone or internet, not even in science fiction. But within a couple of decades, they have become part and parcel of daily life of common man. So it is very difficult to predict exactly what will be the technology, but we can have some idea that in which direction we should be prepared for. It has been attempted to provide a glimpse to the expected paradigm changes in science and technology, leading to the third industrial revolution, manufacturing technology playing a very major role. That you have to keep in mind. The third industrial revolution will change the society to a level that is even beyond the imagination of your science fiction writers. As I mentioned just now, even in 80s, science fiction writers could not dream of anything like internet or mobile phone. It may not happen tomorrow, but India should take initial preparatory actions so that we do not again miss the center stage role when the world faces the onslaught of the third industrial revolution. So friends, I think I will stop here. So at least, and in case you have questions, you can send through your chat to the organizing team, and whatever possible, whatever the degree possible, I'll respond to your queries. And I'm extremely thankful to you for your attention. Thank you very much.
Thank you, sir, for the. It was a very good introduction, starting from the history of manufacturing, briefing about the manufacturing, and then what should be the future of manufacturing, need for miniaturization, self-intelligence in manufacturing, self-assembly. That was a really a wonderful experience for all the audience which are listening to you. And I hope most of them be having some questions they want to ask you. So I request all the participants, if you have any question, you can post them in those questions in question and answer section. And we will mail it to the sir, and the sir will definitely reply those questions there. And with this, we will take a few minute break of say 5 minutes. And after that, there will be another session from the sir. And in that session, that session will be regarding the scaling laws of manufacturing there. So I hope you can take a break for 5 minutes, then we will again come back. Thank you very much.
Let me know when you can start.
Yes, sir, we can start, sir.
Okay.
Yes.
So again, good evening, dear participants. I think so far I have been discussing about or giving or presenting an overview of manufacturing and the extreme futuristic possibilities I have discussed. Now there, I have been every time emphasizing, you maybe have been disgusted that why I'm talking so much about miniaturization. So, but I think you will find that miniaturization is an extremely important issue, and that should be one of the major aims in developing futuristic processes. So now, in this lecture, which is I'm calling as scaling laws, the science of miniaturization and engineering of the future. So therefore, I will discuss what are scaling laws and why we take up the topic in a course related to advanced manufacturing. Now, the scaling laws are quantitative relationships of various parameters of a system with its size. Scaling laws also reveal the invariance of a system. You know, these are very interesting things. As you will see, there are amazing things you will emerge from our discussion. Now, scaling laws deal with the structural and functional consequences of changes in size or scale among otherwise similar or isometric structures or organisms. Scaling laws make the designers aware of the physical consequences of downscaling or upscaling of machines and devices. In the previous presentation, this evening, the importance of miniaturization has been discussed. It has also been presented how this miniaturization is the route to the impending third industrial revolution. However, without proper design of the miniaturized systems, these may be totally non-functional or improperly functional. This lecture is a brief exposure to the basic ideas about scaling laws which should be considered by designers. Now first let us have a quick look of the various types of objects with their scales in the nature. So you can see the living matter, the viruses. This is the size, 1 angstrom, 1 nanometer, 10 nanometer, this is 1 micron, this is 1 millimeter, this is 1 meter and so on. So virus belong to that nanometer level, to hundreds of 10 to 100. Living cells, they go up to 10 micron. Human hair is around 100 micron, and human at all ages is 1 meter. Meter ranges. So materials will be, the sand grains are in this millimeter level. Devices, chips are, sizes are this. Then interconnects, current technology, silicon technology, then these are the nanoparticles and molecules and so on. So this is just a quick glance over the kinds of scales of our objects. Now it must be remembered that designing miniaturized systems cannot be done successfully depending on our common engineering senses based upon our experiences with the usual surrounding. The performance of miniaturized devices and systems will be successful only when the scaling laws are taken into account. Now, how this importance, it's a very funny story, how the importance of scaling was recognized and who started the ball rolling in the development of the subject. It's a very fascinating story. And I think though it is slightly, I'm digressing, but as I mentioned, the talk should have some material for you to relax. This will be something like that. We have to make a journey in time to go back to 1590 AD, Florence, Italy. See, As in many other areas of modern science, the subject of scaling laws got started by the father of modern science, Galileo Galilei. It all started in a very funny manner. You know, he was delivering a public lecture as an aspirant of the position of the professor of mathematics at Pisa University. And there, to get a professor's position, one had to give a public lecture in front of the Grand Duke. So Grand Duke of Tuscany, he was giving this lecture. He wanted a professor's position. And the typical system used to be one has to take a popular topic and to give a lecture on that. So one of the topic or other important point in those days, or a lot of debate used to go on, you will laugh at it, it was how the hell looks like, what is the model of the hell? It was a very popular topic in those days. And Dante gave the model like this, that this is the earth, and a cone-shaped material from the earth has been scooped out, and it is covered here, of course, and this is Vatican. And this space is actually called the hell, where all the criminals go after their death. However, no, the originally Antonio Manetti, sorry, he gave a detailed model of the hell. So here is the deepest level and various other levels, and a thin cover here. Depending on their degree of crimes, they go to different levels. And this was a Florentine philosopher, Antonio Manetti, gave this, which was very popular in Florence. But however, this plan was opposed by a Sienese scholar, Alessandro Velluttolo. He said, no, hell will be only in this region, and this is solid. He said that main objection was, this was of course much later, that how a thin cell can be kept here, because so therefore to protect the whole thing falling down, you need a lot of material. So hell will be much smaller. So there was a big debate, and Galileo took this point. He knew very well that he has to establish the Florentine model, get the job, because then people will be happy that yes, we are correct. Now in his characteristic style, Galileo first praised the opponent's logic, that the shell of the earth covering the hell would be too thin to support itself without collapsing. But then Galileo came to his point, giving the example of Brunelleschi Dome. Those of you who have gone to Florence, you have seen the famous cathedral there, Florentine Cathedral, and famous is the Brunelleschi Dome, which has no problem supporting itself and established the correctness of the Florentine philosopher's proposed model. The audience and the Grand Duke were happy, and Galileo got the job. You can see this is the Brunelleschi Dome of Florentine Cathedral, and the design is like this. Here you can see it is a thin shell, and Galileo said that if this can support, why not the cover of the hell? But much later, when he migrated to Padua and Venice, he was given the responsibility of, because Venice being a maritime civilization, they depended on ships. There, while shipbuilding industry he was examining, he realized his blunder. He observed that ship models were strong, but the full-size ships often broke when out of water under their self-weight. He then studied the strengths of beams and their different behavior at different scales. He also observed that thin ebonite sheets could float in water when divided into small pieces. The matter of scaling laws dawned upon him, and he discussed it in his last book, Dialogues on Two New Sciences. But he kept his mistake at his young age. at the age of 21, a secret to his heart and never told to anybody else. Then he studied the animals and he found that, the big animals had disproportionately thicker bones compared to smaller animals. And he studied a lot of things on this subject, and this subject grew. Now you see, our intuition is based on our experience with the surrounding environment and is conditioned by the sizes we see or feel with our common sensory perceptions. As size or scale changes, different physical phenomena change in their relative predominance, which I will show you with some examples. As a result, system components characteristics also change differently with the size. These changes can be predicted with the help of scaling laws, and system design can be accomplished when the size changes significantly. So for example, when we have some size, then physical phenomena A and B will be predominant at this size. When you scale it down to this size, maybe physical phenomena C and D will be predominant. When you further scale it down to this size, then physical phenomena E and F are predominant. So at different attributes scale differently in their relative importance. The configuration of the system may look very different at different scales, which I will show you later. What can be inferred from the performance of an existing system about that of a system of similar configuration but scaled down to a much smaller size? Now the answer to this question is provided by the scaling laws, and thus these laws play a very important role in designing microsystems. The performances of different subsystems scale differently. Say actuator performance can scale in a completely different way from the structural strength, for example. Thus, the configuration or even the look of a system can be very different from that at a different scale. Now, as a brief introduction to scaling laws will be in order now. And so therefore, what I'll do, I first start with the simplest of the scaling laws, the geometric scaling, which will be very simple, and perhaps you are all aware of the things. Now, geometric scaling is isomorphic. What is isomorphic? Here, the relative size or relative dimensions remain unchanged. So a square will remain square only. A isosceles triangle or an equilateral triangle will remain equilateral triangle. But if the basic dimension is changed, like say this is x, this is 2x, so then what will happen? This area of this, when it's double, scale is double, area gets 4 times. That means area of geometric shape scale as L to the power 2, L square. Similarly here, it is x, you make twice x, so you will find this will be 4 times that original thing. So in geometric scaling, as you can see, that the area scales as L to the power 2. Now we can use, say for example, a similar geometrical figure's area. Now for example, this is a more complex case. Suppose a irregular figure like this, area is A, and this is the characteristic dimension. Now if you scale it up without changing the shape or without distorting the shape, say this L into D, then B will be equal to L square into area of figure A. If it is 2, then B will be 4D. So now therefore you can see the scaling laws can be used also to prove some very standard things. A quick proof of your Pythagoras theorem using geometric scaling. So this is a right angle triangle ABC. You draw a perpendicular to D. So then now we have 3 right angle triangles, ABC, ABD, and BDC. All are right angle triangles, but their shapes are similar. That you can easily realize. So therefore, you can see that the x is the length of hypotenuse. If you take hypotenuse is the characteristic dimension. X is the length of the hypotenuse of ABC, main original triangle. Y is the length of the hypotenuse of triangle ABD. and Z is the length of the hypotenuse of triangle BCD, smallest one. Now these triangles are similar, hence the areas will scale as the square of their respective hypotenuses. So as area of ABD plus area of BCD triangle is equal to area of ABC, we get y square plus z square equal to x square. Pythagoras theorem. Very simple. But I think we can extend it. There is nothing new to you. But if I tell you now that there is a right angle triangle, you all know that if you draw a square here, you draw a square here, and so the square of this will have the area sum total of the square on this plus 1. But if I now tell you that very irregular shape A here, and the same irregular shape is drawn here, keeping the shape same, then also you can say the area of this irregular geometrical shape A is equal to the area of this shape B and this area of this C. That by simple scaling law. So these are, but sometimes you can have non-isomorphic geometric scaling also. For example, if you have a square, A by A size, area is equal to A square. If you make it B, then area 1 is equal to B square. That you all know. Now this is a circle. The diameter is 2A. Area is pi into A square. Now if you compress it and make it an ellipse, and this is 2A and this is 2B, from scaling law you can say area of this ellipse is equal to pi AB without going into integration or integral calculus. Directly from scaling law you can prove that area. Now scaling can be of two types. One is isomorphic, where the proportions are maintained, and allometric. In isometric scaling, the proportion remains the same with the change in size, so that look will be same. But in case of allometric scaling, the proportions between different elements of a system change with size. So the study of changes in proportion of various parts of an organism or system, as a consequence of changes in size is called allometry. So that means P is a parameter, this is a constant, and S is the scale, B is the allometric exponent. This is the general rule for scaling, as you will see, and the next few slides I will come to. Now, for example, I'll give you what it happens when it happens. So isomorphic, this is suppose a water tank of spherical shape supported by a column. In isomorphic scaling up, it will look like this. But if this is scaled up allometrically, you will find that this will look disproportionately thicker. Now it is actually, if you go to nature, you will find that happens. This is because of the scaling laws. Why? Because the weight which acts on this, that scales as L to the power 3, whereas the area supporting it scales as L to the power 2. So when size increases, the weight increases faster than the area which it can support. So therefore, area has to increase at a faster rate, or the diameter has to increase in a faster rate than the diameter of this. So it will look disproportionately thicker, That is allometric scaling. Now, various types of forces. Now, whole matter I'm discussing here ultimately leads to the design of microsystems. So that you have to keep in mind that only while you are designing a microsystem, your scaling laws are important, and without giving proper or taking proper care of the scaling laws, your design may be imperfect and may not function. Mechanical systems are subjected to various types of forces during operation. Some are the motive forces supplied by the actuators to make the machine or the device work. Some are developed as resistance to the movements of the system. Common types of forces which you will encounter, one is surface tension, which scales as L to the power 1, because it is the perimeter length which is important, because surface tension acts on the perimeter. Electrostatic force or fluid pressure force scales as L to the power 2. inertia force, electromagnetic force, weight, etc., they all scale as L to the power 3. So in a graphic way, I can show this, that the surface tension force, van der Waals force, electrostatic force, and gravity or weight, or electromagnetic force also. So there, if you plot it, you will find the scaling is very different. Gravity scales as L to the power 3. As the size is increasing, the force increases, or the weight increases, or gravitational attraction increases as L to the power 3. The electrostatic force, as you can see, it scales as L to the power 2 square. Whereas van der Waals force or surface tension, they scale as L to the power 1. Now its effect is very clear from our daily experience also. For example, let us case this. A different phenomena can be observed with changing scales, though the physical laws remain unchanged. Say, if you have some water in a capillary tube, if you invert it, you keep the open end of the capillary tube downwards, water will not come down, which is very commonly seen. You have to really make it a jar. Whereas if you go to a glass of water and invert it, the whole water will flow. Why? The simple reason is that the water is facing two forces. One is the gravitational pull downwards, and restraining force is the capillary or the surface tension. So you will find the surface tension scales as L to the power 1 and gravity force scales as L to the power 3. So at a very small scale, gravity has reduced much drastically than the surface tension. So sometime what we'll find that surface tension will really overcome the gravity, and so water will not fall. Whereas here, gravity force is much more, and the surface tension at this scale is not enough to hold the water, so it will fall. So though the laws of nature are same, but the outcome of the phenomena, they are very different at different scale. So now we see perimeter area ratio. Now Galileo noticed that ebonite boards could float in water when in very small size. Now let us see this. This is a square board with size A, and another board of size A by lambda. Lambda is the scaling factor. In case of A1, the perimeter is 4A, and so you can see perimeter is 4A and area is A square. So 4A by A square is 4 by A. In case 2, perimeter by area is 4 into lambda by A, because perimeter is 4A by lambda and area is A square by lambda square. So it will be simply 4 lambda by A. So therefore you can see perimeter which controls the surface tension and area of a board controls the downward pull, that's the weight. Bigger the board, bigger the weight. So P by A ratio dictates whether which will be predominant, the surface tension or the gravitational pull. That will decide when it is going to flow, like this. So this is the board. This is the board. The upward force is acting all along the perimeter is the surface tension and the gravitational pull. So here it is much less. But here you will find gravitational pull has reduced drastically compared to this, because this scales as L to the power 1. So ultimately it depends on that perimeter by area ratio, and that you can see downward weight is rho density per unit area of the board, rho into A, and surface tension is sigma into perimeter. Sigma is the surface tension upward force per unit length of the perimeter. So therefore this ratio, rho by A by rho by P, that if you plot, you will find that it will be like this. It is proportional to A. Rho A by sigma P is proportional to A. So as the size increases, this ratio also increases. So when this is more than 1, That means the gravitational pull is more than the surface tension, it sinks. And when the surface tension is more, body force. So you can see the small water bugs can walk on water as shown in the left. But this gentleman, if he stands on water, he will sink. But it is the same water, same atmosphere, everything same. Why it is the same thing? Because the surface tension is keeping its weight, which is very small in case of this water bug, and it is capable of holding it. Whereas this gentleman is pretty heavy, but he could do the same thing. That means this gentleman could also stand in water. But to make the surface tension enough to prevent him sinking, in his foot edge, perimeter of his foot must be 8 kilometers. Now you see again another point for design of mechanical system. One very simple case is deflection of elastic bodies under self-weight. Now this is a beam, cantilever beam, deflection delta, downward direction, and it is self-weight means the body weight is distributed over this. Length of the beam, cantilever beam is L. So as you can see, the deflection is weight L, so these are all solid strength of materials cases. Ultimately, you will find the deflection at the end is proportional to L square. So the deflection scales as L square. When size is large, deflection will be much larger. Therefore, smaller beams behave as much stiffer compared to large beams. Like you have seen that a rod which is mounted on some truck going in front of your car, they just move like a flexible object. Whereas the same shaft, when it is in a smaller size, it will behave like a gramophone pin, will be much stiffer. The same thing which Galileo noticed, that bigger things tend to deflect more. Like if you have a simply supported beam, and he saw that the beam becomes, keeping the proportion same, if you make it larger and larger and larger, after some time, the beam is going to break under its self-weight. Though it looks same, the proportions are same. Now the maximum bending stress, which happens at the middle, is m by bd square, and maximum bending moment is L square, proportional to L square bd. So the stress, maximum bending stress, is proportional to length, L. That means if you plot the maximum bending stress against size or scale, it will be a straight line passing through 0. So therefore, when it reaches the limiting value of the stress, it breaks. But below this size, it is not going to break because the stress developed is much smaller than the limiting stress. That's why beyond a certain size, the similar proportion object breaks under its self-weight. That's what Galileo's observation in the shipbuilding industry. Actuator design for large force development. I mentioned about this, that why in the previous lecture, there nature always takes care of or rather uses the advantage of the scaling laws. Now I will give a very simple example to demonstrate the advantage of using the scaling laws as done by nature. How the choice of actuation system affects performance. Now here let us see, let V the total volume provided for an actuator device, and let F be the total force developed by electromagnetic actuation. Suppose you fill up a motor, electric motor, how much force it develops is F, and the volume of that motor is V. Now, if you reduce the actuator size by a factor n, so the volume of each unit becomes V by n cube, because volume scales as L to the power 3, and the number of actuators that can be placed or packed inside the same space is n to the power 3 n cube. But if you reduce the size by 10, volume of each unit will be 1000. So you can pack 1000 units in the same volume provided for the actuator. Now each actuator develops a force F into L to the power minus 3. If you are using electrostatic, then it scales as L to the power 2. So therefore, if you have scaled it by n, then each actuator is going to scale as n square. So therefore, the total force developed by the actuator in case of the normal electromagnetic case, there are n by 3 to the case, and F is equal to F by n to the power minus 3, n into minus 3, not 4, 3. So it will be simply F by n, as you can see. Sorry. Now you see what happens in nature. Nature always functions. All natural objects, yourself, you're including the participant's hand, we always function using electrostatic phenomena because of ion movement, not electromagnetic. And electrostatic force scales as L to the power 2. Whereas inertia force, electromagnetic force is scaled to the power L to the power 3, as I just shown. Now, say electromagnetic force or the common actuator like motor or something, it develops force F. Now miniaturize it by a factor n. So number of actuators you can pack inside is n to the power 3. And each actuator will produce now not F, but it will be reduced by n square because electrostatic phenomena scales as L to the power 2, not L to the power 3. So each one is producing F by n square force, and there are n number of 3, n to the power 3 number of actuators. If they are massively parallel and functioning simultaneously, what will be the total force? Each one is producing F by n square, and there are n to the power 3. So F by n square into n to the power 3 n. So if you have miniaturized this actuator by 1000 times, the total force it will be able to generate the same volume of actuator, which is miniaturized and massively parallel, will be 1000 times that. That's why a crocodile can snap its jaw in a fraction of a second, producing huge amount of force. Whereas your mechanical device, if you try to make it fast, it will produce less force. If you try to make it very slow or large force you want to develop, then it will be very slow. So nature uses this kind of thing, and in future, all microsystem or micro actuators in engineering function with the help of electrostatic phenomena. This is one example of miniaturization's advantage. Now the actual actuator is not miniaturized, that is macroscopic scale, but its elements are miniaturized to take the advantage of scaling laws. A few examples of allometric power law for complex systems. As I mentioned, many complex systems follow simple scaling laws, and sometimes they reveal some fundamental property of that which otherwise is very difficult. Now, let us consider the phenomena controlled by the surface area by volume ratio. Now, surface scales as L to the power 2 and volume scales as L to the power 3. So, S by V, surface area by V, scales as L to the power minus 1. That means if you make an object small, then surface area will be increasing at a much faster rate, or surface will predominate, or all physical phenomena which depends on surface will be predominant. Say for example, I will show you some example. Like say for in case of animals, which heat loss is proportional to the square of the size, that is surface area, but the heat generation is proportional to the volume or metabolism. So therefore, very small animals, to maintain their body temperature, has to eat very frequently because they are losing heat very fast because their surface area through which they are losing heat is disproportionately high. Many other engineering phenomena we see. S by V ratio effect of scaling can be observed in our daily experience. So white hot small chips from a grinding operation cools down very fast. Why? Because the size is very small, amount of heat inside is very small, but the surface area is very large, disproportionately large. So they lose the heat to become cool very fast. So by the time they fall on the ground, they have lost their temperature they started with. Similarly, you find that there are dust particles are moving around or floating in the air. How? Without falling, this dust particle has the same density of a piece of stone. So why a piece of stone is not falling, but dust particle is flowing? Mainly because this dust particle is so small that its surface area is disproportionately large compared to its volume or its weight. And The surface area controls the frictional force provided by even a small flow of air. So the small flow of air which you have will keep the friction force acting on the minute dust particles floating, and its weight downward is disproportionately small. So the dust particles float. Again, as I just mentioned, large size animals eat less frequently, whereas small size animals have to eat very fast. So metabolic rate and body mass, how they are proportional, that will be shown. And as I will show you, it is a very interesting phenomenon. And that has revealed some fundamental thing. But before going to that, I'll show you how size versus species number of species in our world, and the size, how they are related. Now you see there are small species, small size species are very large in number, whereas large objects like elephant or blue whale, there are very few species are there. So, and again, the living things cannot be smaller than some minimum size, because then the surface tension, Brownian motion, etc. will make their life impossible. Whereas an object cannot be very large on ground, because the gravity will limit their large size. It will be impossible for them to function. Whereas in water, the gravity is less intense because of the buoyancy. So in water, objects or living objects can become bigger. That's why blue whale is much bigger than the elephant. Now, how scaling helps to unravel some hidden secrets of complex systems. Very interesting example I'll show you. The heat generation rate in the body of a living entity is proportional to metabolic rate, and it must be lost through the body surface in order to maintain a stable body temperature. So metabolic rate B is proportional to surface, which scales as L square. Again, the body mass is proportional to the volume. Thus, M is proportional to V is proportional to L cube. Hence, L is proportional to n to the power 3, n to the minus 3. Using this, we finally get the body metabolic rate should be related to the body mass as follows. I'll give a better example. This is better. Suppose this cube, surface area of the cube is 6L square. Volume of the cube is L cube. Mass of the cube is rho into L cube, rho being the density of the material. If B be the metabolic rate, then the rate of heat generation is B. To maintain a constant body temperature, the rate of heat rejection through the surface must be equal to the rate of heat generation. If H be the rate of heat transfer, then 6L square into H, that is the total heat loss from the surface, is equal to B. Or B is equal to 6L square into H. Now L square, again, L square, as you can see, is nothing but m by rho to the power 1/3 from this. M by rho to the power 1/3. So therefore, here directly you get B is proportional to m to the power 3. So therefore, according to this scaling law, the B and M should be related by this law. But in reality, a very funny thing is found. The B is proportional to, that is, metabolic rate is not proportional to body mass to the power 2/3, but body mass to the power 3/4. Now, this was a mystery for a long time. And, this used to be known as Kleiber's law. You can see such a huge range of objects like mouse, small birds, guinea pig, pigeon, goose, dog, sheep, man, so wild boar, horse, cow, elephant. If you plot their metabolic rate by body weight in log, you will find a straight line, and the slope is 3/4. It's a very, almost a perfect scaling law, 3/4. Now, why it is so? It should be 2/3. Now, much later, and recently only, it has been found that this can be explained. You can see the same Kleiber's law. Metabolic rate is proportional to 3/4. not 2 by 3, as expected according to scaling. Now this has been found to be the case mainly because that all objects or all animals, the fluid circulation system in the body, it is fractal. And it has been proved that because of this fractal nature, actually body metabolic rate has to be n to the power 3 by 4 as actually found. Now there are some very fantastic scaling laws that govern the parameters of all living objects. Now the hidden reason behind that is still not very clear to the scientists, and I am giving some. X is the particular parameter, M is the body mass, and this is the allometric law. Now this lambda is important for us. What is this allometric scaling? Now metabolic rate, I have just now shown it is lambda is 3 by 4. Lifespan is 1 by 4. Growth rate is minus 1 by 4. Heartbeat rate is minus 1 by 4. Length of aorta or height of trees, lambda is 1 by 4, etc. So you can see, say for example, that means all major things connected to our life, they are multiples of 1 by 4. Why it is so, nobody knows. Only metabolic rate somehow has been fixed, but why heartbeat rate is minus 1 by 4? Now you see, lifespan is mass to the power 1 by 4, and heartbeat rate is mass to the power minus 1 by 4. What does it indicate? Total number of heartbeats is independent of body mass. That means total number of heartbeat of an elephant and total number of heartbeat of a mouse will be same in their lifetime. Very important. Now metabolism should be, as I mentioned, but study shows the proportionality. It is 3/4 law, and this is because of the fractal nature of the bloody or fluid circulation system law. This is the fractal nature of the, this has been discovered recently, and that's why you can see it is the scaling laws that reveal secrets of some complex systems. Now another quick example from nature where the role of the scaling laws can be easily observed in relation between height of trees and their stem's diameter. That means if you take a tree and their diameter of the trunk, how they are related. The main trunk of a tree can be approximately modeled as a column fixed at the bottom and the tree at the top, as shown in the next slide. Roughly speaking, the weight of the main body of the tree can be considered to act on this column, and the design is based upon the buckling of the tree body. That is roughly speaking. Thus, the model can be as shown. This is the model of a tree. So this is the weight acting, this is the height of the tree, this is the diameter of the tree. Now buckling load for such a column with the bottom fixed and top free and subjected to a load is given by this is the buckling load from standard text you will find in strength of materials. Considering the column to be cylindrical, the double moment of the cross-section area is I is equal to half into pi r over 4. The mass of the tree M can be approximated as the mass of the representative column, pi r square into rho into L. Rho is the density. And the load P acting at the top can be approximated as P is equal to M into G. So pi r square area of the trunk, into rho into L into G. So in the limiting situation, this can be taken as equal to the buckling load. Thus, equating P with PB, one gets L to the power 3 is proportional to R to the power 2, or radius of the tree trunk is proportional to the power L to the power 3 by 2. That means it increases disproportionately with the height of the trees. So let us see in nature how the tree trunks and tree heights are related. Tree height versus trunk diameter. You can see there is some scatter obviously, but by and large it is following a scaling law, and this scaling law fits the derived thing from this approximate analysis, and R is proportional to L to the power 3 by 2. So therefore what happens, a higher tree, a taller tree will have disproportionately thicker trunk, whereas a small sapling will have very thin and slender stem, as you can see from this. some very interesting scaling laws in nature phenomena, natural phenomena. You look at the heart rate of different animals, mouse, chicken, dog, human. As I mentioned that it increases with mass as mass to the power 1/4. This I have already mentioned. And you can see it fits pretty well in a log. So similarly, some other, like say, various things, they scale in a very funny way. But the most interesting thing is our earthquake. Earthquake is, as you know, is an extremely complex phenomenon, natural phenomenon. So now if you plot the frequency of the earthquake of a particular and the magnitude of an earthquake, if you plot, then how a magnitude 5 earthquake takes place, how frequently they are, that will be given by this. How frequently a magnitude of 4 earthquake takes place will be given by this frequency, very high frequency. That means a high magnitude earthquake are very rare. Now, if you plot the frequency of occurrence of an earthquake of a particular magnitude, it fits a particular scaling law, as you can see, a wonderful scaling law. And still nobody knows how such a simple scaling law for such an extremely complex phenomenon of this. And it is expected that a future study of such complex natural phenomena can give us or need many major important. I think we have to find out the invariance of such phenomena, as I mentioned at the very beginning, and scaling laws actually leads to that. Scaling laws in mechanics is very important. Now, William Trimmer proposed a unique matrix representation of force scaling. I have mentioned there are 4 types of forces. Some forces scale as L to the power 1, some L to the power 2, some L to the power 3, and some special cases it is L to the power 4. So this matrix represents 4 different cases of force law. Now, say scaling of acceleration. How is acceleration scaled? Now that will depend on the type of force. So force also, or acceleration also, will be a column matrix, and scaling will be given by this. Because acceleration is nothing but force by mass, where force is a type of force which you have to say, and this is mass scales as L to the power 3. So depending on particular type of force, this and this product will lead to this. Scaling of time, S is equal to half at square. So T will be this, the T scales as this. So in mechanics, you have to consider these things like force, different types of forces, they scales as this, acceleration scales as this, time scales as this. Now, this can lead you to the power density of a device. What is the power and what is its volume? So the total power divided by total volume is called the power density. Power density scales as this. Now remember, now it is realized painfully by most designers that this is the main criterion on the basis of which you have to design your microsystem, which is the power density. If power density is not properly taken care of, the system will either, if it is electrical, it will burn, or it will get destroyed if it is mechanical or failing. So many MEMS design actually got damaged mainly because power density was not really taken care of. So main thing which designer has to see that the power density of the microsystem which is being designed. So while designing miniaturized devices, one of the most important parameters that needs to be given importance is the power density. Many miniaturized electronic devices have been found to fail mainly because of power fault design and the power density was too high. I will give another example before ending. Flying of objects. Now, flying of objects also obey nice scaling laws. And the lift, which it tells that what is the basic thing is that lift must be equal to the weight so that it can be sustained in air. Now, lift depends on the both speed and the wing area. It depends on the square of the speed and proportional to the wing area. And weight depends on the total mass. So, if W is the weight, A is the area of the wing, V is the speed, L is the lift. So lift and weight must be equal, and V is the speed, is the area of the wing, predominant area. The area scales as L to the power 2, and area weight scales as volume, and volume scales as L to the power 3. Hence, A to the power 3 is proportional to L to the power 6, because area scales as L squared and volume scales as L3. So if you cube the area, it will be proportional to L to the power 6, that is proportional to W squared. So W is equal to L, and lift is given by some constant into lift coefficient into total wing area into V squared. So if you cube this, so it becomes then another constant into W squared, because A cube, as you can see, is some constant into square. Now if you combine the two, you will find straightforward that V to the power 6 equal to with some constant is equal to mass, or M, total weight I mean to say. So here the scaling law is mass of the object which is flying and the cruising speed with which it can move. So it should follow this, that means V should be proportional to the M by 1 by 6. If you plot it in log, you find that it's a fly, it's a bee, dragonfly, hummingbird, goose, eagle, sailplane, F-16 flight, a bit higher speed it has, Boeing 747. You can see the range, and it is following, the cruising speed follows very strictly scaling law, where V is proportional to M to the power 1 by 6. So you can see that very simple analysis can lead to certain very fantastic things. Same thing, cruising speed of various flying objects, starting from Boeing 747 to a fruit fly. They follow V is proportional to mass to the power 1 by 6. Now, I think quite often the directors of science fiction movies make gross mistakes by not taking care of the scaling law. Many of you might have seen the movie Honey, I Shrunk the Kids. The kids are made very small, minute, and by some science fictional method, and the whole story is about it. But there used to be another movie released in '66, which a majority of you may not have seen, but I saw it, and that was called Fantastic Voyage. And this was a science fiction movie in which a team of doctors were miniaturized and injected into the vein of a patient for removing a blood clot at an inaccessible location in the brain. The story was that a very famous scientist was visiting a country and met with an accident in a car, and inside his brain there was a blood clot and he was in coma. And it was absolutely necessary to save the famous scientist. So the only way what they did was they sunk a submarine along with some people, the doctor with laser gun, and they were injected inside the vein, and the whole thing went through the heart. It's a big long story. There was a villain also, there was a heroine also. I went to the location on the brain, which was inaccessible from outside. And with the laser gun, the blood clot was melted, and then they came out and the scientist was saved. But you see, the science fiction writers are not familiar with these scaling laws. They don't know how the people will look at that scale. So the Richard Fleischer in '66, the heroine of the film, he was depicted how he should look and scientifically if she has to exist and how she looked. This was the credits heroine, but actually she should have looked like this. Why? Because that small scale, the surface area must be smallest possible for a given volume to maintain body temperature. And that is possible if the object is spherical. So her body should be a spherical body, because this is for a given volume, surface area is minimum. Head should have been also this. Now the light wave which forms the image on the retina for visual, that will not change. So the retina has to be far behind the actual lens of cornea. So the eye should be like this. Now with that small weight, we will need, the legs should be very thin. So thin because the weight is so less, sorry, one leg will not be sufficient to hold the weight, so there will be 4 legs. So actually the human should have looked like this instead of this. So therefore friends, scaling laws lecture comes to an end like this. It is very important. The importance of the scaling laws is primarily for the design of the microsystems and micro devices, because without proper care of the scaling laws, thank you very much.
The word for an excellent and informative lecture.
Thank you.
Yeah, thank you very much, sir. It shows, I don't know how to fit a scaling law for your experience and the energy. You are continuously talking for about 4 hours. I mean, simply amazing.
Thank you. I will be very happy if the subsequent days the participants participate in the adequate numbers, and they take these lectures are primarily some I'll say introductory lectures, but the real material will come from tomorrow onwards. That's what I think I will expect. I may not be able to listen to all, but I'll definitely listen to some of the lectures, and kindly allow me to join when their lectures start. Okay.
Okay, sir. Thank you, sir. Thank you very much, sir.
And if there are questions, they can be forwarded to me, and I'll pass on the whatever possible answers I can give. As I mentioned, these talks are of very general nature and covers a very wide spectrum. And but still, I think I'll definitely try to satisfy my participants if they have questions. Thank you. Thank you.
Yes,
And
sir.
good
Thank
night.
you very much, sir. Thank you very much. Now for the participants, tomorrow morning, 10:30, we will have a lecture by Professor U.S. Dikshit from IIT Guwahati on the topic simulation and modeling of manufacturing processes. I would request all the participants to join in time, maybe 1 or 2 minutes before, so that you can start from beginning. I could see some of the people, you know, they're telling we came late, we came late. Try not to come late tomorrow. Thank you very much. Thank you, Professor. Have a good day. Good night. Thank you, sir.